Hello viewers. In this video we'll finally begin work on tabular counterfactual regret on the GPU. We did that on the CPU in the F# series, and now we're going to do it on the GPU. And because we'll be doing it on the GPU and merging it with the machine learning library, that will allow us to scale it to far larger games. In fact, using what we're going to show you, we're going to be able to use it on pretty much any game that exists. So I need to figure out how exactly are we going to get started. And then what I'm going to do is, because I'm not feeling very inspired, I'm going to make the CFR folder and the CFR file. And let me just say that I'm not going to spend my time explaining what counterfactual regret actually is in this video. In this video we're going to try to figure out how to actually implement it on the GPU. But if you want an actual explanation of what it is, go to YouTube. No. Okay, this is my studio. I'm just taking a look at the F# playlist. Playlists. How to... oh yeah, here's the web development in F#. Okay, here's the shareable link. Oh yeah, we implemented LDAC, random player for LDAC, counterfactual regret algorithm. Integrating the counterfactual regret algorithm with the LDAC and the game and playing a game versus the bot. Yeah, this is pretty much the aspiration of what we want to do. It's kind of amazing how tiny these videos are. But that's because programming on the CPU is a lot easier than the project that I'm doing here in Spiral. So there's no way I could have done something like this for the current project. Maybe in the future the people will be able to do that, because I'll have paid the way to program the GPUs easily. But we're simply breaking too much new ground in the Spiral series to be able to do this easily. Hence you have these huge videos. Oh yeah, those were the days. Some of these videos actually have a fair amount of views. I didn't realize that they have over an average 100 views. the Spiral videos nobody is watching. Well, maybe in the future I'll get back to F#, who knows. Maybe I'll even make some Houdini videos after I get a bigger GPU. Who knows. So we're going to have to implement the counterfactual regret algorithm, and as I said, if you don't know what this is, just look at some of these earlier videos. Maybe this one, it's probably this one that you want, implementing the counterfactual regret algorithm. This video from a year ago, and this one will be on the GPU. So yeah, today I'm going to have to... basically, I didn't really think about what we were going to do today. Yesterday I was kind of satisfied with that redesign, and then I switched off and ended up thinking about other things. I went to the beach. When I get back it was like 9 PM, and then I played XCOM for a few hours. And right now it's right now it's Friday, August the 16th of 2024, and it's 1:55 p.m. And in the morning, what I was doing was creating the descriptions for the videos that I uploaded, as well as the thumbnails and so on. Also, right now, the video that we did yesterday had finally finished uploading, and it has been rendering for the past few hours. Okay, thankfully. Yeah, now we can actually use this in new timeline since it finished the processing. And what I'm saying basically is that I didn't really have time to think about exactly how I wanted to do the CFR algorithm on the GPU. A few days ago, like I think 2 days ago, or maybe it was 3 days ago, I planned it out at a high level, but now it's time to get bogged down in the lower level details. Okay, in times like this, when you aren't really sure what you want to do, the best thing to do is kind of to sketch things out in code. So sometimes you are really sure about what you want to do, sometimes you aren't. And it kind of helps to maybe make a sketch of what should be happening here. So, okay, let's make this test of CFR. Imagine that we have the algorithm implemented, which we don't. We haven't even started right now. So, okay, let's run this on the GPU. But yeah, we need to open core base, open core Cuda, open core ext, core extended, and we are going to run this on the GPU. Let me just yeah, I've been kind of in touch with the Cuda guys. Let me just show you this email for a little bit. I was kind of asking for a breakdown of the compilation time of the example that I made, and the guy, this Yukini, sent me this, and yeah, basically this is what is happening. It seems like the okay, I have no idea what these two are. But this is how much it takes for the front end to compile the program. This is 1.6 seconds. The NVVM optimizer takes 57 seconds, and the PTX translation takes 54 seconds. And this PTX translation, that is PTX to single assignment, PTX-to-SASS. I was kind of considering maybe making a PTX backend and skipping the C++ part entirely, but it seems that wouldn't help for the long compilation times. I just thought that you'd be interested to know, because I certainly was interested to know where the long compilation times are coming from. I had assumed that they were due to the optimizer, but I wasn't certain until I saw the figures. So yeah, we need to start sketching things out. So what's the most important thing? Like, of course, if you have some kind of game, you're going to be using I mean, if you're implementing tabular CFR on the CPU, you're going to have a hash set, and in F# we could just put in the union types in there directly, and the hash set would do the perfect a perfect job of separating out the different cases, and that makes implementing tabular CFR on the CPU in .NET very easy. F# is a very appropriate language for that kind of thing. Now that we are doing it on the GPU, we have to come up with the hashes ourselves, and these indices, for the purpose of this sketching things out, we're going to ignore the game and just give the indices directly, and every thread might as well have the same indice for the time being. Let's make it something like list int 1, 2, 3, 4, 5. And you can imagine these indices to be generated based on a particular world state in the game. So this might be the player getting the private hands. This might be call, raise, also call, something like that. And for each of these indices, we're going to get some kind of, let's say, action. In fact, these indices, these are actually the trace. No, wait. Yeah, that's that's the internal trace of the algorithm. I mean, what I want to say is, because we are doing things on the GPU, we don't have a stack anymore. On the CPU in F#, these indices would be kept on the stack at every particular node in that the game travels through. But right now we're going to be using an imperative loop to go through the game, so these indices will have to be stored in some kind of, let's say, array. Okay, let's make it let's make a dynamic array. Let's make it the list m and we can just use sa-create. Okay, let's just open the list m sa-create. And yeah, we don't we are going to be using an actual list, so let's we might as well push some things to the list. Let's see. Push. Okay. Trace. Let's make it 0, 1, 2, 3, 4. And in reality, it will be, you know, in the real world, once we do this, the traces might end up being like completely arbitrary. Whatever, something like this. And these are the hash sets that are visited. And besides that, I think the trace will require some other things like the action that has actually been selected. Okay, let's make a few type aliases. Type world state, type action. Okay, let's make this world ID action ID. Type action probability. So let's make this trace. Maybe trace item, whatever. Let's make this world ID integer, action ID integer, action probability float. World ID action ID, and 0 could be, okay, 0 would be a fold, so we're going to have just 1 and 2, and action probability of the selected action, let's make it 0. Whatever, 0.2. Let's imagine the 2 is arrays. I mean, right now I'm just playing around. We have to think about Tabular CFR in isolation. If we tried thinking about it in the context of the game itself, it would be simply too complicated. That's why I'm creating a new directory and testing it out completely separately from the machine learning library and the games. Right now we're just sketching things out. So in actuality, every thread will have a different trace, but an equal number of them. So one thread may have world ID this or this, and there might also be a trace for every agent in the ensemble. And this trace, we might decide to just put in a tensor instead of using a list like this. But for now, this is fine. Then a dynamic list is okay. We just need to get a handle on this. So we have the trace. Imagine this as the agent going through a game and then creating this kind of trace. Then at the end of the game, we'll have to actually give some kind of reward. So optimize, reward. The first player. Okay, let's assume that there's action ID here. So let's see, this is like a fold. So let's see, the enters are all one, and then we have a call, raise, 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 raise. Okay, this is a bit too much. These are too many raises. Maybe, okay, maybe maybe this is on the flop and this is on the pre-flop. Okay, so that's 2 2 4 4. So the stacks would be, so the pots would be 13 on both sides, and one of the players would fold. So let's make that reward of 13. Since the first player is the one that's folding, let's make it minus 13. We're just playing around. Optimize and then trace. We also pass in a reward. For more complicated games, we'd actually every element of the trace itself could have a reward, but here we are doing poker, so that's not necessarily the case. Do we have anything else? Like, I suppose, yeah, we do need a model. This is what will keep all the CFR policies. We need the trace, we need the reward at the end. Yeah, I think this is fine. There isn't much more to CFR than taking the ID for the inputs, outputting the ID for the action, as well as the probability, and that's basically it. And it goes through the game like this, and then at some point it optimizes the trace. And of course, we could just put the reward directly in the trace item, but we won't, not for now. So what we need next are the model and the optimize functions. Let's think about what the model should be. Type model. So, of course, on one hand, we do need the model should be kind of like, the way I imagine it, like, well, we did say it should be an array. So, okay, let's make it a tensor. Open tensor m. Tensor. Okay, let's make it tensor integer for now. And what should that tensor have? It should have the average policy. And that could be something like an array in itself. We could also make that something like a tensor. Or rather, let's imagine for a moment it's something like a static array. Let's say average policy, current policy, that's the policy that's currently being optimized. And this time around we're also going to have what? Something like an adjoint policy, so that we can have the traces be Actually, that adjoint policy, I think we we decided that it's going to be in the trace itself. So maybe the trace should have, let's say, add the joint policy. And I don't think this SA create will initialize it at 0, but it needs to be a policy of zeros everywhere. Oh, definitely. Imagine so let's create the model. Tensor create. Let's assume it will have something like 1 to the what 10. This is 1,000. This is okay. This is 65,000. Yeah, I suppose this is fine, even though we can't really create this kind of tensor, I think. I mean, we could try, but I'm not sure it's going to be... It won't be the optimal representation. So, we could fold this static array into a tensor dimension. Let's see. Tensor, instead of having a tensor, single tensor int, we could have tensor int, and then we could make this a float, and also this a float. And this could be, what, 128. 128, that's just 1 to the power of 7. I mean 2 to the power of 7, or 1 shifted 7. 1 shift left 7. 1 shift left 16. Okay, yes. I mean, yeah, this is how we could have the CFR model. We could have an extra dimension here for the ensemble dimensions. We could, since it's just a tensor, we could put this in a graph. And that would have the advantage of making it easy to initialize. Okay, okay, this is supposed to be adjoint policy, not an adjoint policy, adjoint. And these are like the policy intermediates. The intermediate policy update values that's going to be propagated backwards once the reward is calculated. Okay, so the trace. I mean, we could turn the trace into a tensor. Of course, that would kind of make it harder to just push, but we could do a little helper to make that happen. And also, instead of just assuming these action IDs, we should just take the world ID and then get back the action ID, the action probability, and I guess the Android policy. Okay, so type policy ID. World ID. We're going to just put the types for the dimensions as aliases because this will make it more readable. Actually, yeah, this is supposed to be action ID. Oh wait. Yeah, okay. We have the action ID, action probability. As for the adjoint policy, yeah, let's make this a tensor. Tensor action ID float. We can make the probability type prob. Now we have the action probability, the average policy, and the current policy, and the trace. Yeah, why don't we also give the trace a type? Okay, let's put it like this. Type trace equals. Yeah, well, why don't we make it a tensor? Tensor what? World ID. Trace item. No, wait. This isn't the world ID. This is just the sequence ID. The world ID is in the actual trace item. Type sequence ID. And this doesn't really need an alias since it will only appear here. This is the sequence, and then we have the trace item. And yeah, we don't need the trace item anymore. I suppose we can just put it like here. So we now have the sequence ID. But we could also, since we have these nested tensors, and whenever we have that, you can merge them together separately. So let's, for example, we could do it like I mean, okay, this isn't really what I was aiming for. I mean, okay, tensor sequence ID, action ID, that's what I meant. So here we have, or here we have a tensor of sequence ID, and then here we have a tensor of sequence ID and action ID. We just need to organize it a bit better. So honestly, this doesn't look that bad right now. It's pretty much all that we really need from the trace, and because we have these aliases, it's kind of informative what the dimensions should be. Like here we have the sequence ID. I mean, okay, here we have the action ID, and we know that it is related to this action ID here. If we instead had the int here and int here, it would be very confusing. And we know that this is a probability as well. So if we simply like apply the sequence ID here and apply the world ID here, yeah, then we can just add these two together without issue. Okay. I mean, okay, let's make some. Okay, let's make this. Let's make some sizes. You know. And ID equals what? Okay, this is 1 to the power of. I mean, 2 to the power of 16. Model, yeah, this is the world ID, then the action ID. To the power of 7. Action ID, and what else? Oh yeah, world ID, action ID, and then what? Sequence ID. And there isn't actually anything else. And we could have, like, okay, for Ladakh we don't need a lot of sequences, but we can do with the 16. 2 to the power 4, that's 16. And for Ladakh we don't need that many actions either. Like, we can also have only 4 actions. And they need to be a power of 2, and then they'll be masked out. But for now, let's just go with a power of 2. And the world ID, whatever, we can make it, let's go with 4000. There are only like 500 public states in Ladakh, and if we go to 4000, that will kind of make it less biased. There'll be less sequence conflicts. With dictionaries, we'd never get any sequence ID conflicts, but over here we will, since they'll be randomly generated. We can only really reduce the odds of them occurring, but not eliminate them. Okay, so yes, this works as a sketch. Creating the model is simple enough. Let's also make the trace, trace. And okay, I need to raise the table. My hands still. They pretty much never healed. I just kind of gotten used to them using various tricks. I'm pretty sure that this health issue that I've had with repetitive strain injury is due to something in my shoulder. Because now that I'm going swimming, it started hurting, and I feel that's kind of somehow linked to the hands. It's simply the worst. I cannot even work without having issues. So okay, create tensor create and size sequence. Okay, this is going to be size round, size action, and unjoint policy. Okay, that's tensor create, and then what? Size sequence ID, size action ID. Okay, in addition to this, we do need some kind of trace counter. Okay, we no longer need the trace isn't going to be a dynamic list, but a tensor that is allocated on the host, rather these two tensors. We need a counter. Okay, let's enroll C. Okay, let's make this a reference. Ref_m. Alright, 32, whatever. And now, let's ask ourselves, how are we going to push into the trace? Let's make inner push. I mean, we only have a single trace, but whatever, let's pass it in. Trace. Yeah, this trace is kind of assuming that we only have the world ID and the action ID. And no, wait, this trace is only assuming that you have the sequence ID, and in this case the action ID. But every thread will have a different trace, so thread ID. And we're not going to even think about the ensemble, different traces for each ensemble. Okay, so this is the thread ID. Okay, and the thread ID, that's just threads per block. I'm not going to make a big deal out of that. And okay, we're not going to apply them right here. Wait, the tensors, that's way too much. That's gonna make things way too complicated. Okay, let's pass it in. Here we have the C, and let's just okay. Let's open FM. Reference, an integer reference. Sorry, I got interrupted for a moment there, and then I took a little break. I've been thinking maybe instead of trying to actually use this with real money, I could do something like set up a subscription service and make a poker room. I mean, not really a poker room, but like a poker game, something like that costs $5 a month, where people could play against superhuman poker agents. So something like that. I mean, it could be worth a try. Like, just to get some pocket money. Maybe I'll get a few people subscribing to it. I mean, even if like, okay, 10 people subscribe to it. I mean, it's not that it won't be that much, but that's still like extra $50 and if 100 people subscribe, that would be a third of a salary here in Croatia. I mean, typically people try to get away from superhuman agents, but maybe if I, try to inverse that desire, so and build something like, here's a poker room where there are only superhuman agents, and you can play against them without going broke in their real poker rooms. As you can do this as training, then maybe that would get some interest. I really don't want to get stuck trying to compete against the defenses of real poker rooms. I really should be doing programming and ML research rather than try to be something like a black hat. I mean, it would be another thing entirely if I had an actual AGI or something, or on that level. In that case, I'd burn them all to the ground. But these algorithms aren't that great to begin with. And maybe doing that kind of subscription service would allow me to actually get some data about how good real players are. Like, if it turns out that I build such a game and it turns out that real people are losing massively against them, then yeah, whatever, we could play with real money then. I have much more reason to do that then, but without that, who knows. And yeah, that would give me a chance to go back to the F# series, maybe build a... okay, I mean, since this is on Python, we could do it on... Yeah, we have to do the backend in Python, but I mean, and we also want to be running these models on the user's computer. So maybe the subscription would be to download the models themselves. I don't know. We'd have to think about it. The problem with the subscription service where everything is running on the server is that the server GPUs are expensive. So like if we had like clients constantly running GPU queries, that would be very expensive. But if I was running them on their host computers, that would be easy. But if they were running that on the host computers, then that means I'd have to share the trained models and have them download those to the host, as well as the source code to run them. That would be annoying. Okay, let's not think about that too deeply. I mean, I have my desires, and with this level of algorithmic sophistication, my desire to really compete against strong human players isn't that high. I have my responsibilities, which is to pursue the singularity. So I feel that unless I conquer poker, I won't be able to move on to games of even higher complexity. But I know that it's very difficult to actually do what I want. So a partial victory is better than defeat. We'll see. We'll see. I mean, I should at the very least be a little bit of an entrepreneur. I mean, this idea does have some potential for evolution. Like, we could start off with superhuman players, then use generative AI to make maybe anime girls, and then have people play against those. Maybe make some kind of a gacha system. Maybe even add a story. Yeah, that could be pretty fun, I think. Like, it's important to like not every person would really be interested in just playing against superhuman players. So I could make that one aspect of the game, and maybe adding some actual gameplay, like a story, make it an RPG. That could broaden the appeal. Okay, sorry about the digression. It kind of happens that my father knocks on my door and needs some chore to be done, and I decide, what the hell, instead of continuing programming, I'm going to do it now. But because I do that, I kind of lose track of. It gets me out of the zone. I should have just continued doing this, but I'm not really that much into this. I mean, here you have the push trace. Do you feel like doing the push trace? Not really. Instead, okay, let me think. Suppose we just have the world ID, and we want to get the action ID and the action probability, and we don't need the adjoint policy anymore. We just the adjoint policy now is just the thread ID, the sequence ID, and the action ID. Okay. Okay, let's make something like get action world ID It's really, when you're sketching things out and not really worrying about things, it's amazing how clean the code ends up being. So we have the world ID, and then we kind of need to return the action ID. Okay, action ID and the probability. And I mean, we could do that. Like, okay, let's take a look at the model. We apply the world ID. And yeah, now we have the action ID for yeah, and well, we're going to assume that every world ID is different for every thread. So what we need to do is maybe use the row gather and then reduce, I think. Sorry, I'm kind of getting lost in thought. You know, maybe making it my line of business, something like games with RL. Yeah, maybe the way forward that kind of meets all my desires. Okay, focus. Let's go into the primitives. Okay, here's the row gather reduce. Local mass, softmax, and discrete sampling. Okay, I see. I was just thinking that it's about time that we implement regret matching. And the regret matching is instead of using a softmax, we do a ReLU, then we do L1 normalization, and that gives us the probability distribution. Then we can sample from it. Okay, let's take just a short break and then we'll start work on the regret matching kernel. It's going to be very simple to do. Okay, let's work on the primitives. Yeah, it seems we have a bookmark here. We also have one here, we don't need it. Okay, what we're going to do is implement regret matching, local regret matching. So let's see, how is that done? I really wish instead of using this, we could do the reductions using using the option types. Of course, that turned out to be an issue last time, but maybe we could just convert them back and forth in place. Yeah, I'm just thinking what we could do if this is like the option instead of bool. Yeah. I have to use undefined variables. Okay, never mind that for now. It's possible to actually implement this reduction so it uses the optional types, but I don't feel like doing it right now. It's not important. So this is, so here's the local softmax. It's numerically stable because we are calculating the average and subtracting it before doing the exponential. The unstable version will be something like this without the average calculation. And thankfully the local regret matching is a lot simpler. I mean, it's a lot simpler way of getting a probability distribution. What did I do? Config X. Okay, and whoops. Now what do we do here? First, what we need is to take the value of each of these values. And what is the value? I guess it's unbound. Value is simply max 0. That puts a lower bound on these values. Now, once we've done that, we calculate the sum. We have this. Typically, when calculating the L1 norm, we should be taking the absolute of these values. But since they're all positive, since we have just set those negative values to 0, that doesn't matter. We can just take the sum, and then you can imagine what we're doing here. We normalize it by that value. X, if sum is not 0, then x divided by sum, x otherwise the length. I mean, this is not the length, but the inverse of it. Local regret matching. Okay, and this will give us a probability distribution. I mean, I have no idea why we're even using the softmax. I mean, the policy gradients needed, and I guess it works best with the softmax. I've tried the different things other than the softmax. I tried different cost functions, but it turns out log likelihood ended up working the best. That was such a huge waste of time. When I tried doing actual research in RL, I really went nowhere. And for Tabular CFR, we don't need a softmax. We can just use regret matching. That works really well. It's very stable too. I mean, trying to optimize a neural network using policing gradients, using actor critics is incredibly unstable. For something like the game of Go, or maybe for other kinds of board games which don't have a high reward variance, it might work. But for poker, which has insane reward variance, it works incredibly badly. And as far as I can tell, it's impossible to fix it. The fact that we are doing multi-agent RL makes it work that much worse. So tabular RL is the only answer. I think tabular methods are the only good thing that actually came from the entire field. And I got tricked. I should have focused on tabular methods end to end from the beginning, but I kind of got sucked into the deep learning hype, which is doubly more so embarrassing because even going into it, I didn't believe it. I didn't believe in it at all. Yet there was simply no other choice, so I did it. I mean, I know that if I used evolutionary methods, I wouldn't be able to get the efficiency needed to make them work well. Evolutionary methods really require a lot of CPUs to process the games, and they also require a lot of GPUs. And I think the first problem was the biggest one for me. I knew that the CPU GPU setup would lead to a lot of inefficiency. So I thought instead of using evolutionary methods, we should use deep learning, but kind of use maybe find some better models which have better sample efficiency, so we don't have to run many instances of the game to train it. That was a huge mistake. I couldn't find anything at all, either myself or in the papers, and I ended up flaming out. Okay, so we have the regret matching. Okay, so what we're going to do is copy this local mask average, local mask softmax, and we are going to have local masked regret matching. And what we need is to calculate the mask. Okay, fine. We also need the mask. What's this DMT? We need I, a J tensor. Not the other. Okay, we have the mask. I mean, yeah, we do need it. And okay, so local map zip x mask. Oh wait, no, not here. I want to do that. Here, fun x mask, if mask then max 0x, else 0. Yeah, not bad. Now we can also get the mask, although wait, it's not. Okay, and this. Oh crap. We should be counting the mask instead of using this for the inverse. Okay, I guess the mask, the softmax, has an issue. I'm going to show you what it is. Now let's go here. Okay, let's suppose we do this. Let's suppose we do like this, maybe this. Output sample reduce. Output op map. Okay. Okay, let's make this mask softmax, and this is going to be okay, so giant tensor. And we're going to have to work a bit to show you how the error is occurring. Let's close this. Okay, over here you don't see the error, but that's because in this pathway it's still working correctly. We have to okay, what I'm going to show you. Let's do inner x local map, and this is going to be const negative infinity. X Now, once it takes the exponential of this, what's going to happen is that it's going to be 0, and then once it sums that up, it's also going to be 0. So if it tries dividing by that, it's going to cause trouble. So okay, let's try running it and we'll see what happens. Maybe we'll get nans everywhere. Unfortunately, we do. Okay, so how about minus 30, something like that? if we do this and run it, yeah, this works. I mean, I guess it either works or we just get nans everywhere. Okay, not really what I had in mind. I mean, if the error that I had in mind is supposed to happen, instead of this being 33.3 or, I mean, 1/3, it would be 1/8. That's what I wanted to fix. But it never really gets to this path to begin with. So, okay, let us think just a little bit. Like, we have the mass softmax. I mean, here it calculates the average. Negative infinity minus negative infinity. Okay, what is negative infinity minus negative infinity? I mean, is that an n or something else? Why is it opening the sidebar? Oh, for fuck's sake. Let x equals infinity f minus infinity f. And if we run this, yeah, that's negative infinity. So I guess this should be negative infinity. And x divided by, I mean, negative infinity divided by negative infinity. Okay, then that will probably be an n. Oh yes, it's an n. So that's where the problem happens. I mean, but it's kind of a weird situation. I'm not sure what to do with it. Wait, I mean, okay, this should be 0, I think. Then the sum here is 0. 1 divided by... so this line is... Okay, sorry for the digression. I don't want to trigger this error and figure out how to actually do this case where, for example, on the local softmax has very small values and ends up being... Yeah, I mean, compared to something like regret matching, where you could easily get zeros everywhere, it will be a lot harder to actually get that kind of result in the softmax. It's a lot more stable. So I guess we are going to maybe print this out. Console, alright, ln x. Sure, we get the nans here, but what about here? Oh, I do get a bunch of them. Wait, so here is x equals nan. So these are positive. I mean, I'm kind of confused with what are those. Let's also print out the thread ID. Did call thread. So wait, why does it go through this twice? During the first pass is nan. Oh wait, maybe right. We need to disable the other kernels. Now, if we run it, what do we get? In the output we get nan. Here we get this. The only real question that I still have is why is it printing this twice? I mean, did you change back to? Did you set the transfer block back to 32 in base? Cuda base. Yeah, it's 32. So why is it running it twice? I don't understand. Why is it running it twice? Suppose we disable even this. What happens? I mean, I think it shouldn't work. Let's disable all this. We didn't. Yeah, now it prints out none. If I include this input, no. Seriously, what the hell? Why is it printing everything twice? I'm really confused by this local masked softmax. Yeah, I find this very hard to understand. It keeps printing this out twice. I mean, what? Oh wait, maybe it has something to do with it being in row gather map. Like, is it possible that it's executing this twice? Okay, I guess there's something wrong with the row gather map. Yeah, this is what you get for not doing enough testing. And if there's something wrong with row gather map, I guess there's also something wrong with row gather itself. Alright, okay, I think I get it. Like, yeah, as we split, yeah, we have the 8 inputs. The inner dimension is size 8. We factorize that by into 4. Then it gets split into. Basically, what's happening that every thread first takes care of the dimensions 0 to 15, and then in the next loop iteration it takes care of 16 to 31. So yeah, that's why this is printing things out twice. Yeah, so okay, at least I understand that. Okay, we understand that now. It's not a programming error. Okay, so over here we get a negative infinity. Okay, let's print out the average. I mean, that one should be the same everywhere. Average. I mean, what this should be is negative infinity. Okay, so this is negative infinity, the average. And x minus the average. Okay, let's print out the x again. I mean, this should be zeros everywhere, but I think we get nans for some reason. I need to understand why that is the case. Yeah, we get nans. So, I mean, only this part could possibly result in a nan. But really, why? Okay, let's print it out right here. Yeah, here it's negative infinity. R. Yeah, this is an n, but negative infinity minus negative infinity. We already concluded that in this F# script that okay, negative infinity minus minus negative infinity. Oh, so that's how it is. So is this really an n? Oh yeah, it fucking is. Damn. And so negative infinity minus infinity is still negative infinity. But negative infinity minus negative infinity is n. I mean, I guess it makes sense because it's the same thing as this, and that kind of goes into the negative infinity direction. But once I put it in the positive infinity direction, it ends up being 0. Okay, now we are really learning something about floating point arithmetic here. I mean, I didn't know about all these edge cases. So what exactly do we want here? I guess, I mean, if this R is nan, maybe we could set it to 0. I don't know. Maybe we should assert that this isn't an n. I mean, we don't want the average to be negative infinity. I mean, I don't know. This is such an edge case because, you know, if you get negative infinities as the inputs to the softmax, I guess something went wrong with the model. In that case, okay, okay, here's what we're going to do. we're going to implement this like so, and we're going to get rid of this len thing. And the softmax, the sum of the softmax probabilities is pretty much never going to be 0, so it doesn't matter. Like if every input to the softmax ends up being minus negative infinity, we're just going to get nans at the end anyway. So there isn't much we can do about that. Maybe we could check whether this is nan and set it to something, but fuck that. Compared to regret matching, what this experiment made me realize is that the softmax is a lot more stable as long as the inputs are in a decent range. As long as the inputs aren't too crazy. Maybe we should make some kind of assert that the average isn't negative infinity, or maybe that the probabilities aren't negative infinity. Yeah, but this inverse length isn't doing as many favors. So okay, let's get rid of it. And in fact, the reason why I'm checking whether this sum is 0 is pretty much because I was doing the same thing in regret matching. exp x minus average. Let's just inline it here. But I'm kind of worried. What if what if, for example, the values end up being too spread apart? Then, I mean, the average could be something like 0. Yeah, I mean, in that case, one of the values will end up being very large after taking the exponent, and it will end up being 100%, something like that. Okay, I guess this is all a lesson. It's not really... I guess this is all a lesson why we shouldn't be using the softmax, because when the softmax itself is stable, the exponential function isn't. It would be very easy to give it an input that's too large or too negative. I mean, if it's too negative, it would just be negative infinity, which would be 0. But if we try to passing it a value larger than 30, it would just be positive infinity. So, but we aren't going to be using the softmax anyway, so it doesn't matter. What matters is that the regret matching is stable. Okay, so okay, let's think about the regret matching. We got externally sidetracked messing with the softmax. Okay, now we're back to regret matching. And suppose we pass in all the just the zeros as inputs here. I mean, it may happen that at the very start the policy action probabilities are all 0, so something needs to be done in that case. Okay, let's put a bookmark here, go to the next one. Local masked regret matching. And now let's build the file. Oh wait, we're still passing in the negative infinities. I didn't mean to do that. I meant to just pass in a 0. And let's also print out the outputs. OP map. Oh yeah, now you see the issue. Like it's outputting 0, it's outputting 1/8 everywhere as a probability. It's even ignoring the mask. Oh, okay, I mean, it ignoring the mask isn't exactly what I had in mind to really demonstrate, but it's fine. Okay, let's see. The inverse length. I wanted this to output 1/3 everywhere when okay, masked average. Okay, I guess, yeah, we need a count. We need sum. You know, one thing I'm wondering about regret matching is why don't we instead, instead of just doing a value, it might be better to actually calculate the average and then take that as a policy. That would be interesting. Somehow, I don't think I've ever seen that in any of the papers. Never mind. Okay, let's pause here so I can think about how we can do this efficiently. I mean, okay, we can do it inefficiently. Like, okay, here we have the count. This is the actual length after all the values have been masked out. And then inverse length could be 1 or count. And we can also convert this to a float. Yeah, this will convert the integer to a float. And we also have to only have this being like so, where zip mask if sum not equals 0, then x divided by sum, else if mask and sum not equals 0, otherwise, damn it. If not mask, then 0, else if sum not equals 0, else invert length okay, let's try running this. It's kind of doing maybe a superfluous reduction, but there's nothing we can do about that. Yeah, this is the kind of outcome that I had wanted. When the probability distribution is all zeros, then yeah, it masks it out. Okay, I cannot doubt that this is correct, but it's very inelegant. So, one elegant approach that I could think of in order to fix this is to make this mask 0. Instead of having this max 0 be, well, 0, it would be the next highest value that's close to 0. I'm not sure what that is, but if we look in the C++ numerics delta, and if you look at maybe okay, I mean right now I'm kind of wasting your time, but I'm just wondering how this could be done. Not this, no. What I'm looking at for are the limits. And I'm pretty sure that C++ has a function to get the delta of the next highest float. So we can start at 0 and then get the delta towards the positive infinity, and that will give us the smallest number that is bigger than 0. Lowest finite value of the given type, man. Okay, this is one question we should ask Bing. How do we get the value closest the float value closest to 0, but not a 0? Oh, next after, yeah, something like that. I'm kind of wondering how this could be done in .NET. From 0 to 1, I guess. Okay, so what the hell is this? Math apps. Okay, I have no fucking idea what this is supposed to be. Okay, it's easy enough to do it in C++, but I don't want to mess with this. Also, setting this using the something other than 0 for the probability will end up adding a tiny bit of noise into the strategy averaging. So instead of taking that approach, what we'll do is if sum not equals 0, then we're going to in fact do the entire testing outside the loop. But it should be fine because the sum is the result of the reduction, so it should be the same everywhere. Local map. And no wait, we shouldn't be returning the yeah, we shouldn't be returning tensors from if statements. God damn it. Okay, let me go have lunch. We'll resume it later. I think I'll just do what I want and then we'll just skip to the end. I'm done with lunch. And after some thinking, I realized that I actually cannot write this any better than this. It's kind of ridiculous that this is the optimal form, but it is. I mean, maybe we could do this. Instead of a division here, we could do a multiplication, but whatever. I want to leave this readable. And these micro optimizations are best left to the compiler. Like, we could do x times sum and do 1 over sum. And you know, we have to make sure the check here would be right as well, but I don't want to deal with that. Okay, so the local mask, the regret, does work. Let's see, what are we going to do? Okay, let's repeat with JTensor. Fun J, convert J. Let's run this. Now, all the probabilities should be in the first and the second action. The first action should be 33 and the second the 66, I think. Yeah, this is what I expected. Okay, perfect. So the 0 case works and the other case works well as well. Now, what we also want to do is, instead of just the local masked regret, we want the regular version as well. So we want the local regret matching. Yeah, okay, so I mean, is this really fine? Max 0, sum 1 minus. Oh yeah, we need the count. That's what's not right. Oh wait, yeah, this is right here because none of the values are masked out. So if sum not equals to 0, then else inverse length. Oh yeah, we do have the local regret matching done correctly. Okay, so I mean, let's test it out. Let's see what happens. Local regret matching. We got to get rid of the mask. And in fact, let's just copy this. We'll put it here, we'll comment this out. And we don't need the I and the J tensor. Now let's see what gets printed. So the first one should be 1.8, the second one should be, I mean, the first one should be 0.8, the second one should be 1.8. Yeah, this second one is twice the first one, and this one is twice this one. Yeah, it makes sense. And this should sum up to 1. I mean, let's make absolutely sure that it does sum up to 1. Let's fire up the F#. List sum, Alt Enter. Yeah, it comes up to 1. Oh, not bad. Let's try running this. I mean, since we're only evaluating 3 elements here, some of the inputs are going to be all zeros eventually. Yeah, it's probably this one. These are, I mean, over this here, probably the inputs are all negative. Okay, nice. Yeah, this works. I have no complaints. Oh, so we do have the regret matching kernel. Now we can go back to sketching. Even though we'll be going to the beach soon, let's try doing a bit more for the day. Yeah, main. Yeah, we need well, basically we need this. Local masked, regret matching. Okay, what's the input? The input is the model, I guess. And specifically the current policy. Okay. Model reshape on current policy. What the hell? Oh wait, not reshape, but rezip. And the output, well, we do need the output somewhere. And it's kind of really a pain in the ass that we're going to have to, well, we could also, instead of a row gather map, we could just do a, yeah, we've done a regret matching. We also need to do the discrete sampling step. Okay, let's go back to the primitives. Oh, whoops. Okay, let's shut this down. Let's go back to the primitives. Forget this. Yeah, we need the local masked regret matching and discrete sampling. We need to combine it with a discrete sampling step. Even though it would actually be better if we, you know, kind of didn't and simply. Okay, let's. Local mass average, local mass softmax. Local mass softmax. Yeah, we just need to pass in the result of this into the local discrete sampling. Okay, whatever. Let's just do it. Local. Local regret matching. Oh yeah, this is perfect. It's amazing how useful Control D is. I press it once, and it starts selecting the other ones below it. I don't know how I could have lived without it. Okay, so let's see. Let's go into the primitives. Let's this. Wait. What's going on here? I guess we need row gather reduce. And this doesn't take an output. And primitives. ML primitives. These useless type errors fail with. So what's this supposed to be? Intent float. Okay. So this thing here only returns a action ID. And this is the ID. Oh wait, it isn't. What the hell's going on? Oh, yeah, I think we need the render number generator state. Okay. Okay, let's make one. We have it here, in fact. Let's bring it in. And png tensor i32 i32 f32. No, so this is, yeah, this is pretty convenient. Okay, probes, and we can index into it to get the probabilities. Index, tensor index action ID probes action ID. Oh wait, we need to reverse that. Action ID, and then, yeah, not bad. So, oh damn. We actually need that, this tensor. I guess we need to reduce it. Okay, so prob equals local reduce config, and then I guess we'll make the neutral element 0, and then if f1 ab. Oh yeah, we also have to zip it. Yeah, we need to zip the probabilities with jtensor. Limit. Zip x, probes. Jtensor. And now if second action ID, then A, second B equals action ID, then else, we can just return anything. And then we take the first to get the probability. First prob. In discrete sampling, maybe there's a way to. Using a scan sum kind of would lead us to a lot of trouble, and it's better that we just do a separate reduction to get the actual probability. We select the action based on the scan sum, the prefix sum probability, and by that point we aren't even looking at the original. Okay, this is enough to get us the action. We're going a bit further than just sketching stuff out here. And yeah, we should be assuming instead of just returning the second. Instead of just returning the first. Assert I limit max prob Okay, and okay, so we have this, and then what? What can we do with this? Yeah, we need to put in an error message, which is expected valid action ID in action. We're going to put it on a single line. Oh, I just realized something. Okay, now that we have proper closures, we won't actually run into trouble if we just take the action ID from the environment. It should still work, I think. I mean, if we hadn't made those modifications to the spiral code generator, to the spiral Cuda code generator a couple of videos ago, we need to subtract the action ID from all the elements and just check whether the second of A is 0. But it should work like this as well now. Probably. Most very likely. Okay, we have to get action. I mean, maybe this is good enough for one day, who knows. Average policy, current policy, all ID, action ID, adjoint policy. Okay, just imagine this get action is like forget about the actual implementation. We were supposed to be sketching things out anyway. So okay, we have the world ID, and based on that world ID, we can get an action ID and the action probability, and we don't need the adjoint policy anymore, I think. And what we do need is the push function. Okay, so let's think about the push function. We have the trace, we have of course, the sequence ID, but okay, we're just going to grab it from the lexical scope. Who cares? And we're going to pass in the element, which is going to be in the action ID and the probability. And okay, so we have this reference. First, let's extract the current ID from the reference. I mean, I equals sequence ID, and we're going to dereference the reference. We're going to increment the reference, which is then like, I think like this, I plus 1, probably. Yeah, I got it right. Perfect. And okay, now we've taken care of incrementing the reference. We have pushed it forward, and okay, so this is going to be action ID, action prob, and what we're going to do is set something. Other something is this trace. We're going to take trace actions, Okay, I get it. Okay, tensor set. Oh, thread index sequence ID. World ID. I think, yeah, we need the world ID. Let's just copy paste all these. And yeah, this is basically pushing this value into the trace. I guess we could also make something to pop from the trace. We can even make iterators or the trace. And I don't know, it's kind of awkward that we have this reference here instead of in the model, in the trace itself. I mean, it's fine, it's fine. Okay, so let's think about this for a bit. I mean, we don't need the, just like we're not grabbing the, just like we're not passing the sequence ID indirectly, we can just let and then push. And yeah, it would actually be better if we made this a record. Like, what the hell? Okay, let's make this trace element. Type trace element. We had this before, but oh, wait. We're not supposed to be removing all of that. In fact, over here we are supposed to be setting the join policies to 0. I'm just not sure whether I want to do this directly here or somewhere else. Like to do set adjoint policy at I to 0. And we could do this using row gather map, and we just output zeros into the map. In fact, wait, yeah, we can use a row gather map. We pass in the same input and the output, set it all to 0. In fact, why do we even need the yeah, we don't, it's kind of weird. We don't need the input, but we need the output. Actually, I hadn't even thought about that potential case. Like when the from is nothing, but the outputs do exist. Like it's always supposed to be loading something. So yeah, it's kind of an open question how we could do this without necessarily loading from the tensor first. I mean, we don't really need to set the adjoint policy to 0 if we think about it. When When we're calculating the adjoint policy, we're just going to set it to a specific value. And I mean, it's going to be it's just going, maybe instead of calling the adjoint policy, we should call it the policy update. Like, let's do that. Now where is the trace? Thread ID, sequence ID, action ID. Yeah, we're going to be calculating the policy update. And that we just set it to some useful value. Otherwise, the values might as well be untouched. They won't be touched in other cases. Okay, so we have, let's see, trace LM, action ID, action probability, world ID. Why is this giving us trouble? Oh yeah, we forgot to pass in the tensor, so we need the trace and really actions, I guess. But yeah, it doesn't seem like there are trace actions, thread ID, sequence ID. What's the problem? Oh wait, this is supposed to be I. Yeah, and yeah, now we have the push. Now we can accumulate the trace as we go through the game. Okay, and this thing, we should be getting it from the get action. Oh damn, so for fuck's sake. Okay, let's do world ID, world ID. Now we're just going in circles. I'm sorry about this. Action ID. And let's make this get action. And this is the world ID. Oh wait, there was a problem here. Oh yeah, 235. Okay, so what's this? Oh yeah, no. Now we have to convert it. Okay, let's convert it manually to what we were doing before. World ID. And in fact, if you have the world ID, I mean, we could make a smarter push. Okay, let's make this push quote, and we'll do push. This is just going to be take the world ID. Okay, and that will world ID. Yeah, we just pass it into push code, and now we have push what 235. Yeah, great. And now we can just I suppose we can generate the traces like this, but of course we're going to in the actual game we're going to have to get the pass the action IDs back, not just include them in the ID. Not just include them in the trace. But for now this is fine. We're just sketching out a tabular counterfactual regret. And we're going to save here because I need to go to the beach. My mother is starting to urge me to wear my beach pants, whatever it's called. So let's save here. We'll continue working on Tabular CFR tomorrow. And let's just comment this out so there aren't any type errors. This is just in primitive SPI. We don't need this. It's not something that will prevent this program from being compiled in Spiral. It's not something that will prevent this program to be compiled in Spiral. My voice is starting to give out. Yeah, let's stop here. See you tomorrow. We've done enough for Monday. It's a rough start, but little by little the work will accumulate and we'll get something useful out of it in the end. I don't know. I don't know what we'll do after this. Now we have actual, honest to God, Tabular CFR. We can get actions from the policy probabilities. It can be done in parallel. And I guess, the only thing we are missing is to actually propagate the rewards backwards and optimize the model. We're going to work on that tomorrow. See you. Let's start for the day. I've been reading an article about PyTorch and JAX framework. It was it was kind of interesting. At some point I really should take some time to really try out JAX, but right now I'm too deep into this to really change frameworks. There isn't anything like a Spiral out there. So I want to see where this story leads. Who knows, maybe it will lead me to homelessness. Though I hope not. I just need a little bit of success. Okay, let's make this a float. Model, average policy, current policy, trace, actions, tensor, policy update, tensor. Okay. Yeah, when we hover over this, we cannot lose track of what these types are supposed to be. Maybe, like in F#, we should implement type aliasing in the top-down segment, so we get better hover information. But that will have to go. That will have to come later. I simply don't feel like doing that. We can really make we can add things like autocomplete, renaming, type aliases. We can do editor improvements when we are successful. So who knows whether that will happen. But I'll do my best so it happens. Okay, so we have the action ID, action probability, world ID. Whatever. Let's Model trace reward. So we do have a model type. Wait, yeah, this is the model type. I can't believe I missed it. Okay, so okay, let's make the reward type. Reward equals float. Okay. I guess this should come after the sequence ID. No, maybe. Yeah, actually, yeah, it should. We need to know where the end of the array comes, and I mean, we can also just pass this the last sequence ID. Okay. Sequence ID. And yeah, okay, so we have the model, average policy, current policy, and that takes in the world ID and the action ID. And what we need is a loop that goes from the end to the beginning. So let's make a loop. Loop what? Loop for down, something like that. But let's look in the loop module. For down, near, from, to. Okay. To 0. Oh, now we have the body, and we also have the state. For down, yeah. So we pass in the index and the state. Okay. I mean, what do we want as the state? What we want as a state is, yeah, the reward. Not bad. And now, I guess we have to do something to actually optimize the model. Yeah, okay. So during the first pass, what we have to do is calculate the policy updates. And then in a separate loop, we're going to add them all to the current policy using atomics. And then we're going to update the average policy using the current policy. Let me pause here. Sorry about the delay. I had to take a break. Now let's get back to this. So Okay, let us think what is going on. We have to load. Yeah, we have to load the actions from trace. Okay, let's do that. If you look at the trace, it takes in the thread ID and the sequence ID. And the sequence ID is this I here. Okay, let's do sequence ID. In all actions, tensor index. This will be the thread ID and the sequence ID. So thread index, sequence ID, trace actions, reward. Okay, this is just a placeholder. Now we have the action ID, the action probability, and the world ID. So what can we do with that? Well, the action probability is the probability of the action being selected. Okay, now we have that, and the important thing is the world ID. Using the world ID, we'll be able to go into the model and get the average and the current policy. In this case, we need the current policy. So I guess we'll get the current policy. We need all of it. Okay. Okay, let's get the current policy model rezip, I guess, on X, and this is average policy and the current policy. Now we have only the current policy, and we'll index into it. I mean, we'll just apply the first one. We'll just apply the world ID. Actions world ID. And maybe an easier way of doing this would be to just like this. Yeah. Okay, now we have the current policy, and this is a tensor. It takes in the action ID, but that's not what we need. What we need is to calculate the actual expectations. So I think for that we are going to have to extend the model. If you look at back at how Tabular CFR was implemented. Yeah, in addition to just the current policy, we were keeping track of reward values. I completely forgot about that until like this very moment. So the value is kind of the expected value of taking that particular action. Okay, we'll take it one step at a time. Let's make this value, and this will be, let's say, reward. We'll do the rezipping like this. And this will be the current policy and value. And value. Yeah, okay, so this is like this. Okay, so now that we have this, keep in mind, What's going on here is that imagine we have like 512 threads. This is 2 to the power of 9. Imagine we have 2 to the power of 9 threads. Every thread will have the same sequence ID, the same model here, and at the same trace, at least until we apply this thread ID. Every thread, of course, has a different index. Okay, the sequence ID will be the same here, but once this thread index is applied, the actions will be different everywhere. And we can assume that every thread has a different action ID and the world ID. And here we are applying the world ID to the model, and every thread will now have a different current policy and value tensor. So we have a different tensor everywhere. And in fact, well, in order to actually compute in parallel using it, what we need to do is use the row gather primitives, because those were designed so that those that were designed to be used on inputs that have the different pointers but same dimensions. It will speed up the processing. So what we're going to do here is calculate the new reward and then pass it along. It's actually a pretty simple operation. So row gather reduce, and then what? We also use that here. Let's rezip. Let's make it like this. Okay. Config xij tensor. Config xij tensor. And we are passing the model. No, actually, not the model. I'm sorry. Let's name this a bit better because it's confusing. Yeah, we're passing in the current policy over here. Here we're passing the current policy and value. And okay, we don't need the reward. Yeah, we also imagine that every thread has a different reward. That's really key. So okay, but for the time being we'll ignore the reward. We're going to just get the expected value for all the threads and ignoring the special considerations we need to make for the currently selected action. So this is simple. This current policy. Well, to actually get the current policy, I think we need to do like masked regret matching. Okay, local masked regret matching. We need to pass in the mask, obviously, and okay, let's make a mask function. Let mask, because I don't want to duplicate it. We're going to do something more intelligent later, but for now we're still just sketching things out. Okay, this is the mask, local mask, the regret matching, and we're passing the mask, and yeah, we don't need the RNG. We probably do need the config and X. Oh yeah, we need to open the ML primitives. Wait, why is it expecting a number? Oh yeah. We need to unzip it. Okay, in our current policy, and the current policy is different from the current policy probabilities. We need to actually do the regret matching probabilities to turn it into a probability distribution. Okay, so we have okay, how do we actually unzip it? Well, this is just a tensor, so you could just probably do unzip X, maybe. I guess not. Okay, yeah, and value. Oh yeah, current policy. It seems like that works. It's just I'm confused why we're getting this error. Oh yeah, because we're returning a fucking tensor instead of a number. Yeah, okay. And the only thing that's confusing here is why it's showing the error like this. I think it should be, yeah, it's not showing the range correctly. But okay, never mind that for now. So okay, we have the current policy and we have the actual policy probabilities. No, wait, we don't, because we haven't passed. I mean, maybe we need to pass in the I and J tensor as well. Oh yeah, now we have the actual probabilities over here, and we can calculate the expected probability given the policy just by multiplying the probabilities and the values. So doing that is pretty simple. Local map, and we're going to zip the probabilities and the value. And this is fun prob value. Oh yeah, we need a comma here, and then prob times the value. And what we do is do a local sum config. Perfect. And it's this kind of this does calculate. Sorry, this does calculate the expected value, but only for the actions that weren't selected. Because as you can see over here, even though it does a part of the Tabular CFR algorithm calculation, it's not really taking account the given reward and the selected action. So okay, so what do we have to do? Well, obviously we have to take into account the action ID, the action probability, Okay, the world ID, I think we don't need it. Action ID, action, probability, world ID. We're going to do it like this because I don't want to pass this entire. I don't want to pass the world ID into this kernel. So yeah, we have the action ID at the very top, and I guess one thing we have to do is also maybe zip J tensor. J. This J is basically the ID in the array, and over here that is going to be over the action ID dimension. So let's see. Yeah. Wait. No. Yeah. This is the world ID which we have applied, and that leaves the action ID. So what we basically need is let's do this. If no, actually no, not here. If action ID equals J, then something else. Yeah, this thing. And this is the expected value. This is the expected value, and over here we have to basically remember the formula for the tabular CFR calculation. So okay, it's I know that a part of it is okay. Let's do the E equals probability plus value. So this is E. This will also have E, but it's plus E, and on the left it will have it will divide by the action probability. Oh really? And then what? Wait, is this really right? I kind of oh yeah, I do think it's right, and I guess yeah, but this is, I think, is the reward minus E. Did I really get this right? I mean, do we also maybe need to multiply the reward by the probability? Yeah, I think we need to multiply pretty much everything in here by the yeah, I think we need to basically, okay, let's do it. Yeah, and the problem is solved. And if we distribute the multiplications, we'll see that E over here is probability times value divided by the selected action probability. I mean, instead of naming this, well, this is basically the sampling probability of selecting an action, and this is the probability of the action being selected in the actual policy, which can be different. You can use a different distribution to sample an action from the actual strategy, and then what we're basically doing here is simply importance sampling to correct those values for the to the regular distribution. If you aren't familiar with the importance sampling, you can find some videos on importance sampling. Yeah, like here. And they explain it pretty well. And this kind of correction ensures that everything kind of snaps into place. So imagine for a moment that this action probability is equal to the probability here. I mean, this action probability is equal to the probability here. That's what I meant to say. Then we can rewrite. I'm going to just make a tiny explanation. Then this kind of expression would look something like this, and these two would cancel out. So all of this would basically end up being like like this. And yeah, well, what's really important is that if we think about this expression, it's going to be minus value 100% of the time, and it's going to add the probability a certain percent of the time. So imagine this is going to, when the action is selected, this is obviously going to be subtracted 100%, but the actual probability of selecting an action could be something like 1/3. So So 1/3 of the time is going to be adding this probability plus value, and we can kind of drag this outside the if loop, something like this. Yeah, so 1/3 of the time, this is going to be basically added to the value. Imagine this probe is like 1/3, and 1/3 of the time is going to be added to the value. I mean, it's going to be added actually 100% of the time, but it's going to be multiplied by 1/3. So if we imagine if we are doing like 3 steps, like three action selections, this is going to be added like this is going to be added 3 times multiplied by 1/3. So it's going to be like 1. And if the probability of selecting an action is 1/3, then 2/3 of the time this is going to be 0, and 1/3 of the time this is going to be a reward minus value. And these two terms, probability times value and minus value, they cancel out in expectation. So okay, let's do this expected value. Yeah, if this is the expected value, then reward minus value, and this is the expected value. So okay, I hope that this kind of makes sense. And if it doesn't, take a look at some of my older videos, and you can take a look at. Let's see. Let me track down the papers. I think no, not this. Downloads. The heuristics and that maybe RL CFR. Okay, there are a ton of papers here, and I'm going to have to Okay, some of them are deep learning, variance reduction. Oh yeah, this is basically the algorithm that we're implementing. And this is the this isn't the canonical enumerative CFR, but it's a sampling version of it, which also does variance reduction. Amazingly, it was invented in 2018, and it's kind of pretty difficult, I think. And in fact, another paper, not this one, explains that a bit better. Like I really wasn't sure what the purpose behind all those equations are, but it's really just that the value being subtracted and added are just the values in expectation. They cancel out. So let's see, maybe it's this paper which explains it well. Is it this one? I'm not sure. Yeah, it's simply too difficult. I haven't really prepared for trying to explain this. It's kind of very difficult to just zero and yes baseline. Okay, I can't really find it. This is the original paper. I know that I have and I know that in one of the other papers it basically explains what I did just previously, that this value and the expected value can cancel out. So let's probabilities times action. And I want to rename this as sampling probability. I mean, the sampling probability could be anything. We could be basically selecting actions from a uniform random distribution, and that's why we need to use importance sampling here. Okay, I'm going to actually rename this to sampling probability. Model trace reward. Okay, why is this causing trouble? Whatever. Oh, yeah, because we are returning a float. Okay, never mind that. So yeah, and now I hope that this makes sense. We have the reward minus value times the policy probability divided by the sampling probability, and this is just us doing importance sampling here. Okay. Yeah, I think and I think that this is the correct update. I'm going to have to take a look at the CFR code that I wrote in the F# series just to make sure. But okay, for now we're just going to leave it to do double check this. But it makes sense to me, and I do think this is the variance reduction equation being implemented here. Yeah, everything's masked out. Okay, that's fine. So now this is how we propagate the rewards down the tree. Yeah, but right now we're just propagating the values down the tree, and let's see. What comes next? Over here we're just, I think, taking the sum. Yeah, this is the way to. Yes, this is the way to propagate the reward to the next node. But what about actually calculating the policy updates? Okay, I had time to think about it, and I kind of understand where I'm going wrong. I'm going to show you. This is indeed the way to calculate the reward for the next step, but we can separate it out into intermediate steps. So first, let's calculate the updated values. It's going to be a bit different than this. We don't need the expected value, we just need the... Yeah, we won't be multiplying by the policy probability right here. Instead, we're going to get rid of this term completely. I mean, and this 0, even if we multiply that by the policy probability, it would still be 0, so we don't need to touch it. Let's name these values. Expected values. Oh yeah, no, not bad. And these values are actually the key term that we need in order to actually calculate the updates. So first of all, expected. Okay, expected. And it's going to what we're going to pass in here will be expected values. Wait, and we also need the probabilities. We don't need the probes here actually. We just need them here. Policy prob times EV. Oh yeah, we can even, yeah, this is the term that we're going to be returning. I mean, amongst others, we're also going to have to do something to return the actual policy update. And now that we have this expected value, we can do something with it. I remember that when we were implementing enumerative CFR, what we do is basically just do the first iteration of the entire game tree. Then we get to the values, and then we take the expected mean of those values and subtract it from the values. In other words, policy update equals can I name this to something better? Import that sample on the values, something like that maybe. Yes, values. Okay, let me pause here so I can think how to name this. After a lot thinking, I just decided to name these adjusted values. It's good enough. Now we need to calculate the policy update, and that would be local map fun. Okay, first, what do we need to pass in here? Well, we just need to pass the adjusted values. At least I think. Okay. I mean, really? Do we just need to adjust it? I mean, do we really need something like this? Fun. V minus expected value. I mean, is this really the policy update? I mean, I think it would be. Okay, let me think just about this for a bit. Okay, here we have the sampling probability. I mean, if this is 1, then we just get. If this is 1, then these two terms just cancel out, and we have the reward. In the right places we have the value. Yeah, it's kind of probability type has value. Yeah, if we were doing enumerative CFR, I mean, of course, we won't need this expected value here. I mean, we won't need this term at all. Yeah, it would basically cancel out here. So yeah, I mean, it's the same thing. I mean, if we imagine this is if we imagine value to be 0 at everywhere, then it's a non-existent term. And if you imagine this one, yeah, to be reward. Again, yeah, I think this should be right, this policy update, but I have to pretty much double check all of this. Okay, so this is the policy update. Fine. I'm going to have to actually do something with this policy update. Maybe we're going to have to output it in size thread ID, sequence ID, and action ID. Okay, so let's do row gather map reduce. The reward is the input. No, that's not the input. The current policy and value, that's the input to this. And the output is what? Yeah, we need a policy update in our policy update, because is it a part of the model, or is it yeah, it's a part of the trace policy update. We don't need to apply the thread ID and the sequence ID. Trace policy apply sequence ID and apply what? I think it's thread ID that needs to come first. You know, it was really a thread index. It was really a brilliant thing of me to actually put to name the dimensions here, because imagine if these were all ints. I'd forget what they were supposed to be the next day. So this policy update, and this is the output, and it's map reduce, so the map tensor needs to come in first. Yeah, and this will update the policy updates. Okay, I mean, in addition to that, this is not the only thing that we need to actually update. We need to update this this value. This value part of the tensor. This value part might actually even, I suppose we can update it using a moving average update, but we could also keep track of the counts. So I'm not sure what exactly we want to do. I think in my old implementations of CFR, I probably kept track of the counts in places. Okay, so what do we want to do here? I mean, we have the reward, we have the world ID, action ID. I guess we could do the value update as well. This is the thread ID, the sequence ID. I don't think this will take the action ID because we're not updating all the parts of the policy. It's kind of, the policy updates is very unique because it gets normalized, so we don't have to keep track of the counts or anything like that. But over here, instead of doing a vector update, we can just make this a tuple of reward and action ID. And yeah, we're probably going to have to do. Going to have to use a compare and swap to update this. So because it's F32 and action ID, I'm not sure whether that would work. No, I mean, it's not a problem here. It would only be a problem in the... Yeah, the value is only a reward, so we'll be able to use a compare and swap to update it very easily. We could do a moving average update like that. And the current policy will be updated using atomics. I think at the end of all of that, we're going to have to actually go over the entire model and do a max 0. So the current policy is it's a way that CPR updates are made. You can just do regret matching, and this will trim out the 0 elements, but the optimization will be faster if after every optimization pass you also just set the negative values in the current policy to 0. The updates will be faster. You see that trick being used in counterfactual regret papers. I've implemented it myself, I think, in the F# series. Okay, value update. Reward and action ID. Okay, so let's zip this. Policy update, value update. Okay, let's think about the value update. Value update. Value update. Thread ID and the sequence ID. I think yeah, we don't even need to set this in the kernel. We can just set it directly. Okay, how about we do this? Tensor set reward and action ID, and yeah, this is the value update. Okay, this is easy enough. I mean, do we really need to set the extra ID? I mean, we should I think we should have that in the tensor itself. Thread ID, sequence ID. Yeah, we have the extra ID. Yeah. We don't need the yeah, we don't need to put the extra ID separately, because it's just going to be the arrays are going to end up being the same anyway. So I mean, the array that contains the action IDs and the one here. So we don't need to make a redundant array for the action IDs. Okay. Excuse me. Yeah, I do like this. Okay, let's the return type for this should be ignored. I kind of want to make sure that reward yeah, I don't need to put this here. It's ignoring the reward. Oh yeah, this is, I don't know, it looks quite clean to me. It's a very nice implementation of Tabular CFR. I think it's certainly much nicer than I remember it being when I did it in back in Cython, or even in F#. Local map, local sum. Yeah, after you do a programming piece, it's kind of it's a good practice to maybe just sit back and admire your handiwork. Yeah, this is very nice. Oh, okay. Okay. We did this part, but this is just calculating the policy updates and the value updates. it's not actually updating the model. So I think that's what we need to do next. I'm still naming this optimize. We should just name this calculate updates. Calculates the policy and the value oh yeah, this is good. Okay, this reward we can in fact just randomly generate it, but okay, I won't mess with that right now. Well, so what? What do we need to do here? What do we want to do here? What should we do here? Yeah, we need the trace, the thread ID, the sequence ID. I guess we need to go over the value update and the policy update arrays, and then using that update the model. For the model we have the world ID and the action ID in the trace. Okay. We're going to name this apply updates. Second ID, model trace reward. Okay, the action ID the current policy and value, and okay, the current policy and value. It just needs the action ID. Let me place a bookmark here, because it has started to get tedious to go back and forth between. Oh wait, this got the calculate updates. I need the apply updates. Okay, the policy update, the value update. We don't need the reward. In fact, maybe it wouldn't be a bad idea to fuse these two together, like into a single optimize function. But never mind that for now. We'll see how it ends up being. I just want to mentally separate out the calculation of the updates from their application, because since we are in a parallel environment, in a multi-thread parallel environment or a context, it's not as straightforward to actually apply the updates. That's the main reason why we were doing all of this. So I guess, yeah, the policy update requires the okay, the policy update, yeah, it requires the action ID, the actions, and the value update. Okay, when you update, this will now be tensor index. The current policy and value. The current policy and value, they are taking wall ID and the action ID. Oh fuck, did I? Yeah, they're just missing the action ID. Yeah, and what we're going to use now is row gather map void. And let's see. The input will be the policy update. Let's first update the policy. Okay, we don't need to pass in the reward. We're going to make this pour down quote, which is the immutable version. Okay, so you have the row gather void and you have the policy update. We only need the action ID. So we have the X. So we could do something like a local. We don't really have this primitive. We're going to need to implement it like local atomic add X to policy equals where is it first? But yeah, but this right now is not loaded correctly. So suppose we do something like local iter, and then we're going to zip x and j tensor, and this is going to be fun x action ID, and then we can do something like atomic add x to tensor at maybe ptr action ID, something like that. But we don't have a local iter. The atomic add is missing, and tensor ptr is also missing. Okay, so we're going to have to do some work in order to actually implement these primitives. So how are we going to do that? Okay, first of all, let's actually but this needs to be action ID. Let's actually figure out how to retrieve the pointer of the tensor at action ID, and this action ID we need to apply it to the current policy. Correct. Oh fuck. current policy and value. I think that should be all of them. Oh damn. Okay, that should have fixed all of them. I just pressed Control D a bunch of times and then edited the occurrences, all of these out. Yeah, I could have also just pressed Control 2 instead of rapidly pressing Control D. Yeah, okay, never mind. It's good enough. Current policy and value, and we have the current policy, and we need to get the tensor pointer at... I don't think we have something like some kind of function for this, but I can't remember where it was. Okay, let's first check into tensor Cuda. Okay, tensor reference index. Oh, here we have the tensor atomic add. Does an atomic add to the tensor at a specified index by a given value? Oh, okay. Okay, this is so index, value, and then tensor. Okay, tensor atomic add, action ID, the value is x, and the tensor is the current policy. So what's the problem? We need to open tensor Cuda. Open tensor Cuda. We don't have the local iter. We need also the action ID. So yeah, let's just add the local iter. We're going to go into ML primitives, local map. Is this in here? Local iter f from in place maybe iter I mean, where's this local in place map? Oh, local in place atomic add. Okay, that's interesting. I mean, it's interesting, but this operation is pretty useless. I mean, if you load it into a local tensor, what the hell are we going to? We need to be adding we need to be doing the atomic adds, targeting the tensor in global memory. It's useless to do this on a tensor that's in local memory. I mean, the tensors that are in local memory are all on a single thread, so it doesn't matter. Okay, not bad. We have the localiter. Now let's go into what here, and yeah, it's complaining that we're zipping what. Oh yeah, we need to put a comma here. Yeah, and this works now. Not bad. Tensor, atomic add, action ID, and current policy. The current policy. Let's just check one last time. Current policy takes the world ID and the action ID. And here we're applying the world ID. Actually, let's do it like this. Rezip and then unzip. Yeah, this is elegant. Okay, now we've applied the policy updates using this tensor atomic add. It's great that we actually had it in the library somewhere. The way it works is pretty simple. Stride offset. I'm not sure whether I've ever used that, so we're of course going to have to make sure that it works correctly. We're going to be testing it out for the first time. But I think this, let's call it pseudocode, it should be correct. So the one last thing that we have to apply are the values. Okay, so excuse me for a moment. Let's resume. One of the legs on my keyboard got unscrewed. This one went past the limit and fell out. I just had to take a moment to put it back. Okay, so we have the policy update. What about the value update? Okay, we have the action ID. Let's also get the value update, like right here. Value update. Okay, where do we get it from? Model. Yeah, we also have the value update, which is thread ID and sequence ID. Okay, thread ID and sequence ID, we can just tensor index into it. Value tensor index. So this is the thread index and the sequence ID. Now we have the value update. Oh wait, we already calculated it here. What the hell was I doing? Okay, so we have the value update, and we have the value. Okay, so what this one is missing? It's applying the world ID and the sequence ID, I think. Yeah, the world ID, the value is applying the world ID and then the action ID. So maybe tensor set. Okay, this is going to be wrong, but I just want to prime my brain. Tensor set and the value comes at the end. This is the value update, and the tensor we need the action ID as the index. Of course, this is wrong. What we need to do is let's say a compare and swap operation. I mean, alternatively, we could also use something like a moving average. I mean, alternatively, we could also use a count instead of a moving average. That's what I meant to say. And, you know, just normalize it every time, but do I want to do that? I'm not sure. Let's go with a moving average for now. Tensor. Let's make it tensor compare swap update. And this is going to be fun value. And you know, moving. Okay. MA factor, moving average factor. Let's make it like 0.2, something like that. So this will be the old value times 1 minus MA factor plus update value update times MA factor. Okay, and yeah, this is kind of algorithm dependent. Oh, never mind that for now. What we're missing is the tensor compare and swap update. I mean, compared to just doing an atomic add, the compare and swap yeah, we don't really have a good way of doing the compare and swap on compound data types. That's the main issue here. Of course, on a single F32 data type, it should be fine. Okay, I'm going to just make a version of this that works on the default floats, and if that's not good enough, then current policy. Oh yeah, we also have to update the average policy. I forgot about that. Okay, let's go into the tensor Cuda. We have the tensor atomic add, and now we have to take a look at compare and swap operations. Atomic gas, okay, yeah. Unsigned. Oops. So it can only, it reads a 16, 32 or 64-bit word. Global share memory. Only calls compare. 99. So it does have a template version. Let me pause here just for a bit. Sorry, I had to take some time to think. I didn't know that it's possible to use reinterpret cast like this. It's a decent bit cleaner than what we used to convert a float to an int. Okay, oh yeah, I think I understand. Something just occurred to me. Here we only have integers and not floats, but if you think about it, floating point comparisons are kind of weird due to the infinities and nans. For example, a float value that's a nan, and when you compare two float values that are nans for equality, that will return false. Let me show you. Okay, let's select F sharp and nan equals nan F and enter, and this returns false. So that really explains why this function only accepts integers. I thought maybe this was a design oversight, but it isn't. Okay, so let's implement these functions for the 16, 32 and 64-bit word data types. Let me raise the table. It's kind of, my hands are hurting from all this sitting. Well, let's forget about what we are doing here for the Tabular CFR. In fact, during the break I realized that I completely forgot about the path probabilities, so the policy update is not necessarily correct. Okay, let me put a to do. Don't forget about the path probabilities. And we're going to go into intrinsic. Really? I mean, I'm not sure this is the way to do an atomic addition. I think the atomic addition... okay, let's take a look at the atomic add. Oh, it works off on quite a few data types. Regular integers, 32 and 64-bit integers, then float double, then the half data type, but not 16 or 8-bit integers. Yeah, I think we should do these atomic adds properly, instead of assuming that any of them could be used. We're going to get back to this later, never mind that for now. I mean, over here, I guess this was just a shortcut, because I didn't feel like implementing the separate versions at the time. But for the atomic CAS, as you can see, it doesn't have the float data types, so we're going to have to do reinterpret casts for to make it work. Okay, so let's do atomic CAS 16. Inner atomic CAS 16 array U16. Oh, they're all unsigned. Okay. This is the address. So we need to the address. It also does return. Oh yeah, I can't forget that it has a return type. And this is very important, so let's make this U16. Okay, if it's an array, I mean, if it is an array, then it's fine. Do we want an array or a reference here, maybe? Intrinsic refm. No, it doesn't make sense to pass in an array into this. Well, let's pass in a reference. Open refm. I think this should be in intrinsic. Okay, ref. And this is now A, old, new. Yeah, let's do this. U32. Oh, this fucking feature is great. U64. Wow, I love this. This editor is so helpful. It kind of has such a sensible shortcuts and defaults. I don't have to think too much about configuring it. Okay, so I mean, do you want this to be something like ref, or do you want to keep this naming scheme? I'm not sure. I'm also wondering how we are going to do the 128-bit. That one is a templated function. How could we possibly do it? I mean, we don't even have any 128-bit data types in the language. Maybe float form. Okay, I don't want to have to think about this right now. We're going to make use of this. In addition to this, we need okay, let's do a reinterpret cast. I want to at least assert that the sizes of the two types are equal. Okay, let me think. So we're going to be converting the floats to U32s in order to be able to use the atomic CAS. In fact, let's make a generic version of royalty. Oops, we also need oh no, wait, I don't want this. What exactly do I want? I wish I could implement a generic version which does the proper conversion. I mean, if size of something is 2 or 4 or 8 or 16, then do the atomic CAS. How do we handle the return values? Yeah. Okay, never mind this for now. Let's go into the. Where are we going to do the? Yeah, in tensor Cuda, I think. No. Okay, let's just prototype the function that I want here. We're going to do the big function. CAS. Yeah, we don't need the old and the new. Instead, we're just going to have f t to t, and this is going to be returning unit. So we do need. Okay, let's check the size of t. I mean, let's do this in the bottom-up segment, maybe. okay, let's do it like this. Let's go through all the cases individually. If size of t value equals 2, actually let's mention this, match with 2, then we're going to okay, let's do a while true, a loop while const true x, I guess we'll I mean the reference, or wait, do we need to for fuck's sake, let's just let's make this an array. Then inl x, yeah, I mean is a 0. Inl x array interpret cast value u16 yeah, here we do an reinterpret cast. This is old. We need to get the new. Okay, so how about this? Oh yeah, like f old. And this also returns the, how I put it, old, and if old equals old, if the compare swap operation succeeded, then loop break. Basically, if, so for example, here we'll load the value from index from the array, then we do the map operation, and if that map operation, and if then we pass those values to the atomic cast, and then we check if the compare swap succeeded by comparing the old values, this old with this old. If these are equal, then the compare and swap succeeded, otherwise it failed. Of course, as you can imagine, one of the necessary ingredients for this operation to succeed is that this f be functionally pure. And then this whole thing makes sense. So this is when it's 2. Okay, let's oh wait, we don't even need to pass this into here. Instead, yeah, this returns a unit. I mean, we don't even need this. It should be obvious. This is T. So what's the problem? Oh, it's unused in the function's type signature. I see. Yeah, what exactly do I do here? Maybe we can just pass in a phantom type. And yeah, we have to yeah, this is how we apply the phantom type. And the phantom type is if you look in the core base and base, I think we have it at the bottom. Oh, here it is. Phantom t equals unit. It's pretty much nothing. It just allows us to pass types in the top-down segment. So what do we do? Yeah, we can take care of the other cases like this as well. U32 64 and if it's 16, then I'm not sure what. I mean, we could convert it to int 4. And this is an inbuilt Cuda type. Let's take a look at int 4. It's a vector type, I think. Int 4 and uint 4. Okay, let's convert it to uint 4. I mean, do we even need any conversion? Actually, we don't. Like, if it's 16, yeah, then we can just leave it as it is because it has a templated implementation, and otherwise oh wait, I could have just done this. Whew. Not bad. So yeah, this is ideal. Yeah, we don't even need we don't need a reinterpret cast. Okay, we're going to hack the reinterpret cast a little. Okay, where did we put it? If a then x else oh wait, not like this. Yeah, this is how we do type comparisons. So if the two types are equal, then just return the original thing, otherwise do this reinterpret cast. Yeah, perfect. Now we don't have to mess around with this mess. And For the primitive types, it should know at compile time what the right size is. And if it doesn't, the Cuda compiler will know at its own, during its own compilation pass, what the size of the type we are comparing is. Yeah, I like it. I like this a lot. Now we can does an atomic compare and swap. Using the oh wait, this will result in an infinite loop if the asserts are disabled. Oh, I just realized that I had the cursor highlighting turned off. Sorry about that. Yeah, during the break I disabled it because I was watching anime. I didn't want it, and I didn't want it to show up on the screen. I knew I'd forget to turn it off in. I knew I'd forget to turn it off after the break was done. I mean, to turn it on after the break was done. I just knew it. Okay, so this is... I guess this is done. We have the atomic CAS update. Okay, now let's close this. And let's go back to the ML, to CFR. And we need to apply the updates. Tensor CAS update, so that's what we are missing. Yeah, okay. Let's implement Tensor CAS update. Where is Tensor Cuda? We This is in the real segment. Okay, oh yeah, we need FL L to L. Yeah, and it cannot possibly be ether too. This isn't like the atomic add. Yeah, the tensor isn't really the best abstraction for this. Like, can we get the tensor, the current pointer, something like that? Okay, let's take a look at the tensor main. How do we get the tensor, the current pointer? No, wait. Pointer at current offset. I mean, how about a pointer at arbitrary offset? I guess we could do this kind of reorder, then apply the first, then get the pointer. IDIM. We're going to reorder fun x apply I, then wait, I forgot to pass in the tensor at the very start. Reorder, apply, and then apply pointer. So it's like this. Apply, and then we just do this kind of reordering, apply the index, then we apply the pointer, then I mean there's no need to flatten it. So we're going to do pointer at, and then we're going to pass that into the CAS update. Okay. We're not going to do anything here. atomic array, atomic CAD. I mean, does it have to be like this? Can't we just... Yeah, instead of asserting the indices, we should just do that reorder and then apply. Okay, I'm just wondering in how many places are we actually using this atomic CAD? Over here. Play. I mean, are we actually using this anywhere? Yeah, we aren't. I forget this shitty function. Because atomics work on such a restricted subset of primitives, we have to be more careful how we use them. Okay, answer Cuda. I mean, this is fine. This is... Okay, I want to clean this up, make it a bit less... T. I mean, why am I writing all this out again? Yeah, we should just use pointer at. Or actually, no, not the pointer at, but... reorder, apply, and then apply pointer. And now we don't have to calculate the offset here. We can just pass it in as it is. And in fact, I'm going to change this entire function. So it just takes an array. We don't need to add the offset explicitly. Tensor class update. Yeah, I think this should be fine. Maybe we should do a particular pattern of applying the pointer. I mean, no, we'll leave it like this, and maybe if we end up doing this in more places, we'll factor it out. It's not a big deal. Wait, I think actually we do have something like that in tensor main. Like, what about apply both? Oh, apply all. Oh, I see. Yeah. Oh, yeah. We could use this. I pretty much never use that anywhere. To my reorder. Yeah, what we should have been using here instead of this, apply all. Yeah, and this is much better. Apply all I and then apply pointer, and then we just do atomic adds. Oh yeah, this is perfect. Yeah, this is how we do it. I don't feel nearly as bad to be copy pasting this. We don't need the offset here, not anymore. We don't need the stride. We don't need to bind this to a variable. Yeah, we can just leave it like this. And in tensor main, okay, so let's get back on track. Let me just check, are there any errors anywhere? Yeah, this, oh yeah, TensorCast update. And we said that we're just going to extract the array and then update in that one, so, okay. First, let's do pointer at. Pointer at action ID, and what are we supposed to be updating here? Yeah, I think the value. And then intrinsic CAS update, I think. Damn it, I can't remember. Intrinsic atomic CAS update. Oh yeah, okay, like this. And yeah, this requires the array to be in the first place. Okay, so so like this, pointer at action ID value. This returns an array. Then we update it. This does an atomic add. It's a decent way of doing it. Oh yeah, we also need to update the average policy after all this is done. So I guess after the policies are updated, I mean, how do you want to update the average policy? That's actually a good question. I mean, you might be wondering why would that be a good question? It's because the way the average policy update isn't very standard. Like, I don't think the way the average policy is being updated in at least the sampling versions of CFR it makes sense, and it kind of does some. Okay, I'm going to have to stop here for a bit and just I can think about this aspect of it. I had to really think about how we could actually update the average policy, and we're going to make some significant changes, and I don't think I like this kind of update anymore. Instead, we're just going to also keep around the denominator and use that to normalize the value. Also, I realized something here, that there's this trap function. Instead of you calling the PTX exit function, maybe we should be calling this the trap function so we could actually abort the kernel in a more, how would I put it, in a more official or standard way. I wanted there to be some kind of indication instead of just a print statement in the console that the kernel has failed. Okay, so before we do anything else, let's just try out the trap function. And okay, we're going to copy this. And I'm just going to compile this and see what comes out when we do a trap. Trap. Now let's build this. And if we run this, what happens? Oh, we cannot turn all these. Let's close all this down. I mean, nothing is happening when I do this. I guess okay, let's try putting a print statement like print f hello. Oh yeah, and the buy never gets executed. So this trap function actually acts exactly the same as the PTX assembly function exit. There's a interrupt is raised in the host program. I mean, it's not really raising any kind of interrupt. That's the only problem with this. Maybe if we synchronize on the device. Occupy CP Cuda device, or maybe Cuda stream. For fuck's sake. Synchronize. Cuda get current stream synchronize. So it's like that. Synchronizes the device. What's that? Let's try pasting that in. I just want to see whether it actually... Maybe it's not showing an error because it exits too early, so... I mean, maybe it's not showing an interrupt because it exits too early. Oh, okay. Oh, I see. So, yeah. Nice. If we remove this, then... oh yeah, this is really nice. I think we should be generating this CP Cuda get current stream synchronize at the end of every Cuda program. So what happens if we, instead of this thing, we instead of the trap, we instead use... okay, let me show you how exceptions are currently generated on the Cuda side. CodeGen, where is CodeGen Cuda? Here it is. Fail with... yeah, it generates this ASM exit. It does a printf and it follows it up by ASM exit. So suppose we replace the trap with ASM exit, would that still give us an error? I mean, it gives us a type error, just not the error that we want. Yeah, okay. Let's do this. Oh, this doesn't generate an error. Oh, I see. Okay, great. I've decided we're going to replace this ASM exit with trap. I feel a lot better about this. So oh, it's the 17th. We've gone a while before the last update. Replaced ASM exit with the in the Cuda code. It will raise an error on the host, assuming it's and yeah, so it doesn't exit before the kernel completes. We're going to put a device synchronize. Yeah, we need to do that in Python code generator. So let's see what's going on. Okay, how do we put a device synchronize? Okay, what we should do is it kind of ends with print main, and that main can return anything, so we cannot really just put it like. I mean, yeah, we could just put it right before the main. We could hack this to get the result that we want. Let me think. Yeah, we could add this at the end of the array and then swap the two strings. Okay, let me think. Main definitions, globals for declaration, functions. Okay, what are the? Oh yeah, these are the kernels. These are Cuda kernels append. And okay, what about the Python? Oh, here's the Python code. I guess that's a string. It calls the code gen. Okay, this is what we are supposed to be looking at. Line start is text append line. Okay, I see. Types, functions. Oh damn! I don't think this would work. This will work. We cannot really. We aren't adding this into an array line by line, but we have these string builders. Okay. In that case, we can also just. We have this print main. We could potentially do like before we end up pushing this, let's just test it out. Let's try running this. Oh yeah, and we also got to put in the trap. I mean, but it should work because we didn't get at some kind of parsing error in Python. Yeah, I very much like this. Yeah, and when it fails like this, it will at least tell me to take a look in the console. If I instead do that fail with and it prints something and then exits, I might not even notice something going wrong. Yeah, and I mean, I'd prefer to have put this in the at the end of the main function, but I guess it will also do well enough here. It's not a problem, but I'm not sure I want to do this kind of synchronization. I mean, okay, this is a specific Cuda backend, so whatever. I mean, we have default arrays that are CuPy GPU arrays. You cannot even run this backend without an NVIDIA card. So yeah, it's fine to do it like this. Nobody is going to be running the main function from anywhere else. And actually, I mean, sometimes we don't run the script directly. Sometimes we just get the closures. Okay, so how do I want to design this? I mean, yeah, I'd really like to put this at the end of main. I just don't know how. I mean, we could always put it manually. I mean, we could go with this and also put it manually. Then it's a really tiny thing, but it's not really easy for me to find a place to actually change the program to be able to do this by starting this. I mean, we could kind of split these into individual lines and then add them somehow, but I'm not a fan of that. Okay, well, I mean, there is a thing we can do. Okay, one thing, there is one thing we could do, like, we could make this main like so. Then, oops, I forgot that I'm not on Visual Studio Code. Then we make a main like this. And then line indent S and in addition to this, we can also R main and this could be return R. Okay, we could make this main body. Body. Okay, yeah, so like this, and we also add a line. Basically, a new line. Okay, I like this. equals main body, then we cp Cuda get current stream synchronize, and yeah, okay, this could work. So let's try building this. We'll publish a new version of Spiral. This one is not for VS Code Marketplace, but just in the language plugin folder. We're going to try running the extension first and compile it once, just to see that we haven't broken everything. Okay, what was the problem? Oh, what the fuck? Oh wait, I think I probably just ran the extension too quickly before it finished building. It can take a while the first time around, like 20 seconds. Oh, it succeeded. Sorry about that. I need to pay attention. Okay. Yeah, now we have the main body. We're synchronizing. Oh, perfect. Down trapping. And I guess it's, let's see, 1, 2, 3, 4, 5, 6, 7, 8. And yeah, this does look like 8 out of 32. Okay. Oh, this is good enough. We're going to release a new version of Spiral. Yeah, good enough. Let's publish this PowerShell run. And now we'll have to wait a few minutes until it finishes releasing it. I mean, I don't remember seeing the trap function in the Cuda guy before. Maybe it got added recently, I don't know. But I could have maybe simply missed it. My memory isn't exactly the best thing in the world. So yeah, we need to wait for a few minutes and then launch it. But okay, until that happens, we're just going to work in the extension host. It doesn't matter. You know, by the time you watch this video, this will long have been released. Like right now, I have video scheduled 3 weeks into the future, so it will be a while before this one even comes out. Okay. All right. Let me just make a commit. Making progress on parallel tabular CFR. Oh, test 9 pi. Okay, not this. Updates the current policy. Oh yeah, now let's get back to this. As I was saying, I don't like moving averages, so we're going to change the value. So instead of just having the value itself, it's going to be denominator and numerator, or yeah, numerator and denominator. It's basically going to be a value and a count, and we're just going to use atomics to add to it. It's simpler than this. And it's going to be, the beautiful thing about that is that it's going to be independent of the order that we do the updates in. That's why I want to do it instead of using a moving average. And using atomics is more efficient than using compare and swap. And as for this, we're using atomics to add the probabilities to the, or rather to add the policy update values to the current policy. And the problem with that is that I have no idea which average policies to update after that. I thought of what we could do after we have done this, and I'm pretty much stuck on this step. And it made me realize that even though what we're going to do is going to require extra memory, we still need to do it so we can do the average policy update properly. We also need to do it simply because we need to cut off the negative values after each of the updates in the current policy, I mean. And right now that's also impossible. I mean, okay, cutting off the current values, yeah, we can just do a map over the whole current policy and do it that way, but it's... I mean, yeah, we could have done it like that, but in that case we'd still have to iterate over the entire array, so we might as well do this better. Let's go to the top. Mold ID, action D, sample probability. Okay, this is fine. Value update. Okay, reward count. Okay, type. Mold ID, action ID. Oh yeah, okay, yeah, this is perfect. And okay, now let's see where are the type errors. Yeah, here we have the reward, calculate updates, value update. Oh wait, what the hell are we doing here? Oh yeah, why are we doing tensor set? This is just a value update, and we apply it later. Alright. So this is reward, and the count is 1. And now we're getting the values here, and yeah, this is not good. Current policy and value, and yeah, this is a triplet. Why is it expecting this to be? Okay, reward and count, values, local map, fun a reward, count, reward divided by count. Yeah, this is the way we'll be doing this. Instead of using a moving average, we're just going to keep track of the counts. And if you wanted to kind of speed it up, we could just decay both the reward and the count, and that will put more weight on the recent updates. But never mind that for now. Oh yeah, we must not forget the path probabilities. We'll get back to that later. Okay, policy update, value update. Okay, so we have the value update. And what we need to do is tensor add atomic, I think. Okay. I mean, let's do this, just this thing, this little bit, and then we're going to stop for today as I'm tired. Okay, tensor atomic add, and yeah, it takes index and value. Okay, the index is what? I guess it's the action ID. The tensor itself, is it the value? I think it is. No, the tensor is at the end, and what is this? Policy update. It's not the policy update, but the value update. Yeah, the beauty about atomic adds is that we can just we can add all the values of a compound type independently, unlike the CAS, which must be like a 16, 32, 64, or 128 bytes. We don't need this MA moving average factor anymore. Later on, maybe we'll maybe decay the value. Okay, now what we're going to do is also change this. It's going to be easy. Okay, we have the policy update, we have the value update. Okay, let's make this update policy. Okay, where's the current policy? I mean, yeah, we don't need the current policy, I think. I mean, update policy, update okay, great. In fact, can we model? We could just have something like policy, and then we could this could be policy current. Oh yeah, not bad. Now we have policy update and update policy. Oh my god. Whatever. Whatever. Okay, I mean, this is kind of pretty unique naming scheme. We should probably take some effort to name it better. I mean, this should be this should be update policy, and this should be policy updates. Okay, that's oh no, we cannot put this. Okay, I mean, we could do maybe updates and then value. But now I'm only improving the naming for these records instead of the variables elsewhere. And okay, let's do update equals yes. Update policy. Okay, now I guess there really should be update policy, and this should be policy update. I mean, but that would make these things. How do we swap these two variables? Okay, let's do this, and this, and then we'll update policy. Update for the policy and the policy update array. Now let's check this out. Current policy. I mean, we could kind of rename this to policy current. But whatever. Maybe we could change this to the reason why I'm changing this is because this is in trace, so I want update to come first and the policy second. So maybe I should just name this trace update policy and be done with it. Okay. Policy current and value. Okay. Policy current and value. I basically renamed all of this. Update policy. Update for the policy. Policy current. Yeah, keeping the naming consistent is pretty hard. I'm really happy that I found this Ctrl-D trick, so I can just select everything like that. It helps me massively. So yeah, this instead of being added to the current policy directly, gets added to the policy update. And in the next step, what we're going to do is pretty much update everything as it should be. We're going to do a row gather map. No, actually, do we even need to do that? Could we maybe just, if we look at the model, the whole ID, the action ID. So yeah, we're actually not going to do even a gather, but a regular row map. We're going to go over all of these, average, current, and update. We're going to add the update to the current, set it to 0, set the update to 0 at the very end. I mean, actually, when I said set current to 0, I mean take the max of the current value and 0. After the update array should be set to 0. The average array will be updated everywhere that the will be updated everywhere where the current array has actually been updated. So we'll have to do a reduction over this update to check whether any of the elements whether any new information has been provided, and we'll know that by checking whether any of the elements are not 0 across the entire inner dimension, across the action ID dimension. And that will allow us to actually update the average, because we don't. The main problem that I'm having is figuring out how to actually update the average policy based on the current one. Yeah, because I didn't know where the updates have actually been occurring. So I thought, until I came up with this current idea, I thought maybe I need to maintain some kind of array of switches, but that will be so complicated. I will just iterate over this entire model and be done with it. Just screw it. And this value, I guess, yeah, this is getting added to directly. The only thing we can really do is maybe, in a separate step, maybe decay the reward and the count. And by decay, I mean multiplying the reward and the count by the same constant. Something like, it can be like 0.5. And that won't actually change the value. After you divide the reward by the count, multiplying both sides won't change the value, but it will affect how much the old data is being considered compared to the new one. Adding a decay would make this act more like an exponential moving average. Maybe we could just decay it so that maybe the count is, after it's above like some kind of value, like maybe 200, then decay it back to below 200, something like that. It's no problem. World ID, action ID, we have the values. We have the counts. Everything is perfect. Wait. I mean, who cares? Let's not spend too much time formatting this. It's clear enough. Yeah, and we'll leave this work of actually updating doing all the updates in the model for tomorrow. Right now, I guess it's time for me to stop here for the day, have some fun, watch Code Geass, and tomorrow we'll do this, and we'll also figure out how to deal with the path probabilities, because right now the policy update this update policy array isn't being calculated correctly. Over here we have to multiply by the path probability, counterfactual path probability, and we also have to divide by the sampling probability. And by the sampling probability, I don't mean this one. This is just the sampling probability for the action, but we have to divide by the sampling probability of the entire path. And multiply by the path probability of the opponent's path. And that's the way this should go. I mean, right now we're just sketching things out, so I'm not sure how we're going to deal with path probabilities. Okay, let me, in anticipation of tomorrow, let's do just a bit more renaming. Action sampling probability. Well, let's rename it to this. And I'm pretty sure that the only place we're actually using sampling probability is, yeah, in places like these. I know we'll be able to distinguish that from the path sampling probability. And do we also have the action probability somewhere? Action prob. I guess we don't, and we probably should. Action sampling probability. I mean, we can also name this action probability. Oh, wait, why didn't it? Oh yeah, nice. And we could also rename this to action probs. Now that I have this Control D, it's like having a superpower. Yeah, I'm pretty lazy, so I don't feel like clicking this, renaming this, and then having to copy paste everywhere. I mean, if I was programming in F#, I just use the rename functionality and do it that way, but in Spiral I don't have that, unfortunately. Okay, let's finish it here. Did some redesigning. Let's just check whether the spiral has come out. Spiral. Yeah, and it's updating it. And yeah, let's finish it here for today. It's time for me to have some fun. I've earned it. A new day is here, and we'll do some programming. Yesterday we changed how exceptions are being compiled in the Cuda backend as well as the Python backend. We replaced this asm exit with trap. I'm just wondering whether for the missing pattern matching cases, how those are compiled. What we call copilot. Assigning it to GitHub, starting a free trial. Whatever, I'll look into that later. I actually never tried Copilot. Exit. Not the fail with, but pat unbox. I mean, actually maybe just unbox. Tie union unbox. Assert. So we just print out the assert as the default case. Maybe it would be better to also print out a trap. Because the asserts might be turned off, so in that case I still wanted to just eject from the kernel. And if asserts are turned on, this trap will never trigger. Instead it will just say invalid tag. I guess it's fine. Okay, so yeah, this should be fine. So let me just make sure that I wrote this out correctly. Oh yeah, okay. Okay, so we're going to let's test this out first thing, and then we're just going to release a new version of the language. Okay, so match bin some man I32 with some x none. Okay, let's build. Whoops! I didn't mean to run this in PowerShell. Spiral build file. Let me just set up my keyboard. Yes, okay, spiral build file. Invalid tag. Oh, yeah, but this is happening because I forgot to run it in the extension host. Oh yeah, I also forgot to actually build it. Spiral build file, and what do we see here? Yeah, now we have the trap. We can try running this. Oh yeah, I mean, it's triggering this. Oh, not bad. Block thread. Okay, that's good enough. It's good enough for me. Let's release a new version of Spiral. And while that is going on, PowerShell run. Okay, commit push. Okay, now let's finally get back on track. Okay, let's see whether Spider has gotten released. Oh, yeah, I did. Anyway, I had to think a little break to add this to the timeline. I mean, to add the latest clips to the timeline, where you add some timestamps. And we're going to get back to this. Now, I think what I was saying that we do today is do the update. We're going to do that, in fact, because, you know, it's only 10:55 a.m. and we have plenty of time left in the day, maybe to finish this whole thing. The main thing that's concerning to me, I realized something, besides forgetting the path probabilities, I realized that after we do the proper update, this is in fact going to have to use grid wide primitive, which we don't have implemented. But actually implementing it won't be hard at all. For example, let's take a look at the row gather. Okay, not this, but row gather. And over here we have this dim linear block. Instead of that, we could have a projective loop. And we could do blocks in grid and dim block. And basically, all we have to do is replace this linear loop with a projective loop, and the same goes in the in this row template. And that's all that we have to do in order to do a grid iteration instead of a block iteration. The one other thing that we also need to do is, for fuck's sake, where is it? Yeah, here it is. Instead of using this barrier CTI sync, actually we can leave this in, but besides using that, what we have to do is grid sync. And for that we're going to have to use the cooperative group, a cooperative group object. Cuda. Let's go into the cooperative groups, grid synchronization. Oh yeah, this grid and then grid sync. And we have to launch it as a cooperative kernel. And we are in fact doing that, I think. Let's go into the primitives. I mean, we're pretty much compiling everything the same right now. And let's see. Where are the options? Oh yeah, this is what we're using to compile. We set the backend, and we just need to have this be set to true, which it is right now. And that will launch the kernel in cooperative groups mode, and we'll be able to do grid synchronization. I never actually tried that before, but it should work. I mean, we have to modify the kernel so we can pass the grid cooperative group object but that shouldn't be difficult. So I guess we could modify the template. I mean, well, we'll see. Okay, let's not think about that for now. For now, we'll just assume the GPU has only one block and do this tabular CFR implementation in terms of that. It's very easy to. I mean, it's not super easy, but it's easy enough to change this to a so it uses the entire grid. All the hard part is within a block. Yeah, we must not forget the path probabilities. We'll get back to that later. This is updating the value arrays, atomic CAD. Let's do the actual updates for the policy. So in order to do that, what we should do, okay, let's do yeah, for this we don't even need the row gather. We can just use a row map. Let's do a row map. And we'll leave this like so. And for the inputs, what exactly do we need? Average current update. Yeah, we need all of these. Yeah, we need all of these. I mean, if you wanted to decay the value, for example, we could also do that right now. As for the trace, do we need anything from the trace? I don't think so. Value policy. Okay, I mean, well, let's just put, let's just pass the entire model as the input. You know, value decay equals, let's put it 0.95. We'll put in the model as the input and the model as the output. No problem. One config xij tensor. In fact, I don't feel like typing out JTensor constantly. Maybe I should just change that to J and be done with it. Okay, let's press Control F2, J, done. Now, okay, let's see. I mean, yeah, let's do it at JTensor. We're using that kind of naming scheme everywhere. I shouldn't be changing that here. So, okay, so here, if we hover over this, what you should see is that we have the policy average current update and then the value. So, okay, first of all, let's check if inall is update. And we're going to do x reshape x reshape fun x can I just return x here? We're going to have this be a float. Okay, now this is wait, what the hell? Oh wait, rezip, not reshape. So okay, we have the policy, the current update. We just need the update. Okay, so policy update. Wait, why is it giving us? Oh, okay. God damn it. Let's do it like this. We're going to double pipe it into the raw map. And now that we do this, the type inference has more information. Once we cover this, we see that now it has the actual type information, and then is the update. That's now F32. Of course, this is not what I'm aiming for. What I want to do is local reduce config, and then fun AB. Actually, this isn't what I wanted to do either. What I want to do is local reduce or, and we'll pass the false as the neutral element, and here we'll do a local map fun x, and we're going to check whether x is not 0. And this is the bitwise operator. Instead we need the regular one, but that one doesn't work either for some reason. This is weird. I mean, oh yeah, this thing is not a function. It needs to do shortcutting, so we cannot treat it as a regular operator. Because it's the way the OR operator gets compiled is special, so it needs special considerations in the parser. I think that's why we cannot use it as an operator. It's different in something like Haskell. I think in Haskell you'd be able to pass it in directly. Who knows? Maybe we could modify the parser so it gets treated as an operator, but it's not really worth our while trying to mess with that. Okay, so we have the local map. Okay, so let us think. I mean, if it is an update, then if it is an update, I kind of want to use it like this, but if it is update, then we do the update, else we just return the regular model, but I kind of want to avoid doing that. That's the thing, I want to avoid having to return anything from an if statement. Because if we return a tensor for an if statement, the offset, the dimension, and the strides will get pushed to runtime. I mean, one way of actually enabling that kind of functionality is to convert this function to a continuation passing style. So we'd have something like a return, and then we could just do ret here and ret the result here. And this wouldn't have issues with returning from if statements. I didn't think about this at all while I was working on the raw template. I mean, could we actually change that? Could we change this to local map or reduce? Oh yeah, could we? Yeah, we could maybe create a local tensor and then just assign to it and then return that. I mean, it's kind of weird, but it would work. Yeah, I mean, we could just assign to the original tensor, like, I think we have a local map in place. If you look in place, yeah, local in place map, okay, local in place map, and we could just output the final result into the original model. Yeah, that's the perfect solution. I don't know why I didn't think about it, but I simply didn't. So we're going to be returning the model either way, model. And in fact, we could have done this, we could have used this technique in, I don't know, I mean, we probably couldn't. No, I forget what I was going to say. Never mind that. I'm just wondering how the local tensors are created. Like, we have local. It's just tensor create. Oh yeah. Okay, so if we need to do an update, then we'll do the update. So how will we do that? I mean, okay, let's see, what exactly do we need to do? We have the policy average, current, and update. We have to set the update to 0. We have to add the current to the average. I mean, first we have to add the update to the current, then we have to do the renew thing, then we have to add it to the average. we also set the update to 0. We also decay the value. Okay, here's how we're going to do it. Local in place map, and then model to model. It's going to be fun x, and this is going to be policy value, average current update, okay, first let's calculate the new current policy. So in all, current equals, so that's policy update, and we need we need to zip the policy current and the policy update. Zip policy current, fuck it, let's just do this. Average current update, local map, and current update. We have to add the update to the current and take the max 0. So max 0, current plus update. And while we're at it, we can just set the update, I think to 0. Update current and update. And we can also, while we're at it, set the current, add a new current policy to the average. But no. We also need before we add the current policy to the average, we also need to normalize it. So let's do it. Unzip. Why is this causing trouble? Oh yeah, because we're not returning anything. Okay, so average current update. Okay, this is mainly the this is the policy. Policy equals value equals what? I mean, it's just going to be value. So okay, what's the problem? Oh yeah, this needs to be a tensor. Yes. For fuck's sake. Okay, let me just return. Let's just do a fail with. Now, I want to do a double pipe. So we have the type information. This is a double pipe, and yeah, now we know exactly what the types of these are. Why is it giving us trouble? Local map, zip current and update. Wait, what the hell? This isn't supposed to be F32, but oh yeah, this is supposed to be crap. This is supposed to be a tensor. I mean, oh no, wait, it's not supposed to be a tensor. What the hell am I doing? I'm doing a local map inside a inside a map. I'm so confused. Sorry about that, I got confused. Okay, we don't need to change the update here. It's good to know that the current is this. Oh yeah, so yeah, we're going to have to calculate the probability distribution of the current one, so that's going to okay, this is, I mean, it's kind of damn, we cannot add the current to the average right here. I mean, we can just set the current to the new value and the update to the 0. We can also update the value. Okay, which order do you want to do things in? Do you want to... Okay, we'll do everything step by step, even if it takes more than a single map. It doesn't matter that we are using multiple maps. The Cuda compiler will optimize that away, hopefully. I mean, it will inline all the loops, and in that case, it won't matter which order we are doing things in. So, okay, let's calculate the new current. The new current, that's just the model piped into a local map. And then we do fun. I mean, we should also do rezip fun. I mean, I know that I said that what we're passing into the loop doesn't matter, but I kind of want to make it easier on the Cuda compiler. Current and update. Current and update. And okay, the new current will be max current plus update, and the new update will be 0, 0, and zip update. Oh wait. So what's the problem here? Yeah, the meta variables. Float. Okay, so we have the current and the update. Now we need the average. First, we need to calculate the action probes, and that will be we can do that just by regret matching the current. Local regret matching current. I think we need the config. So is this the only thing that we need? Oh, it seems like it. Okay. No, I mean, it doesn't matter. It doesn't make sense. I think we should be passing the I and j tensor. What the hell? Local sum. Oh damn! We need a mask. We should be doing masked regret matching. I mean, maybe not really. I mean, since we need to do the masked regret matching when we are actually sampling the actions, and when we are sampling the actions and calculating the policy updates. But over here, I don't think we actually need to do it. We would need to do it if it was something like a softmax, but for a regular local, for a function that works like this, it doesn't matter if some of the elements are 0. They won't affect the other ones. We are not doing an exponential. You said that this function is linear. I mean, it's nearly linear. That's one of the good things about the regret matching function. I do like it more than the softmax. Okay, so local regret matching is fine. I mean, the only thing we're kind of doing this max 0 thing twice, but it doesn't matter. The local regret matching also checks for whether the sum is 0, and I don't want to have to re-implement it here just so we can avoid doing this max 0. Maybe the Cuda compiler will be smart to optimize that away. So we have the action probabilities, and we'll be adding that to the average policy. So let's do that. Average I'm just making it a bit easier on the Cuda compiler because I'm nice. I'm a nice person. I care about compilers. I care what the compilers are going through. Okay, so action probabilities. Now we have to do a local map. Okay, and local map fun AB A plus B. Is that not it? Oh yeah, we also need to, yeah, we need to zip this too. So zip. Did we forget to close the parentheses somewhere? Yeah, I think we did. Okay. Yeah, great. Now this is average. This is the action prob. We could also decay this average policy while we're at it here. Average decay. But we want to do it. We'll just I mean, let's do a little bit of decay. When you're decaying the average policy, this kind of method is called linear CFR, linear counterfactual regret algorithm. That's how it's going to be called in the papers if you read any of them on this subject. Okay, as for the value decay, okay, so we have the current, we have the update, the action probabilities we have put in the right place. I've just put actual progress inside the statement. So, okay, current, update, average. Is this all fine? I think it should be. So, yeah, the only thing we are missing is decaying the value. Okay, let's get the value, and then we're, value. Oh no, wait, I just realized something. I mean, we don't really want to yeah, we only want to decay the value if it's yeah, I mean, yeah, we only want to decay the value if the denominator is above a certain threshold. Value threshold. So what do we make it? Like, we might as well make it 100. I'm just putting this stuff out there. I think previously, when I was testing Tabular CFR on something like Ladakh, I used a pretty severe value decay, something like 0.5. I found that to work the best. So what we're doing here is actually not something that I ever tried, like putting in a threshold. And the average decay should also have a threshold because we're doing a parallel update. So, okay, let's. Yeah, if we are going to have a threshold, we don't really need a decay. We can decay it to exactly the threshold if we. Okay, so this this is going to take some work. We no longer have a decay. So this average, what can we do with it? I guess, yeah, we should really do a specialized function for this. So let's say if the sum is greater than some value, for this average, then we bring it to the threshold. Okay, so we should do that in the primitives. Local threshold config x. Okay, let's do this. Local sum. Threshold. Unnormalized. I mean, we can do something like a L1 threshold. Like local map absolute x, then we take the sum of that, then we divide by the sum and multiply by the threshold if the sum is greater than the threshold. I guess we need to I mean, this is just a more generic way of doing it. So I kind of want to be absolutely sure about everything. I mean, I don't want to have functions that are too specific in this library, even though it would be less efficient to do it like this, because yeah, now we have to take the absolute of x. Okay, x equals local map absolute of x. And then the sum is the local sum of x. If sum greater than the threshold, then local in place map. Let me just raise the table because damn, my hands hurt. I haven't really gotten over my RSI at all. I kind of gotten used to it. Programming with the pain as my companion is no fun. X. And what we're going to do is x divided by the sum. I don't like having to write out in-place map. It would be better if this was simply a local map quote. Let's see, where is all this being used? Okay, so, oh yeah, we divide by the sum and then multiply by the threshold. You know, I guess we can just factor that out. One divided by the sum times the threshold. And we can just put the threshold on the right. Like this is just basic elementary school mathematics. And now I can just multiply this by v. Oh, we can in fact just do it like this. Oh yeah, no problem. I'm kind of getting the hang of this. And usually L1 normalization is done with a threshold of 1. And that was just that's in fact what we're doing in local regret matching. We're dividing by we're calculating the sum, and once we do that, that ends up normalizing the vector. So the L1 norm is 1. L1 norm is 1. So let's use this. Well, wait, is it a threshold? Yeah. Okay, average threshold config. Great. Now this will decay the average. We also need to decay the value, so let's do that. I haven't actually used, yeah, as I said, I didn't use this kind of decay scheme last time, even though I kind of really like this one. What I did last time was either use moving averages or something of that sort. And yeah, this one is pretty simple to grasp. Oh yeah, I did make a mistake. Because wait, actually maybe I didn't. What I meant to do was also multiply this by the length of the vector, but I kind of forgot that you know, the probability distributions are kind of, you know, from they need to sum up to 1. So if I set the threshold to something like let's assume the threshold is 1. If I multiply that by the length of the vector, it would be thresholding to the wrong thing. So yeah, this is perfectly fine. This average threshold will hold up for 100 updates. The value threshold, yeah. If we keep track of the last 100 updates, and they'll start to decay. You know, the value threshold, maybe we could lower that, but never mind that for now. Okay, so we have the average, now we just need the value. And how are we going to deal with that? So, okay, model. This one is easy. And this is local map fun AB if B value threshold, then you know, even here we don't really need to do it like this. We don't need the local map. We could, if the sum is greater than the threshold, then we do this, otherwise V is 1. And then we don't, we can leave out the conditional check. Yeah, no, this is nice. If sum greater than the threshold, then threshold divided by the sum, else 1. Oh yeah, perfect. I kind of want to avoid the conditional branching in Cuda code. Even though maybe the previous version would have been better, since it avoids yeah, well, let's not complicate things too much. We can just leave it like this. I think this way would be more efficient, because it's impossible that actually no, it's very much possible that this could diverge. The reason for that is, suppose we have only something like 4 probabilities in the in a vector, then every thread will be responsible for a different vector, and the sum could very easily differ. It will be one thing if we were absolutely sure that this that the probability vector that's being handled here is of size 128. In that case, it will get every thread, every warp would be operating on the same vector. But if that's not the case, then in fact avoiding conditional branching is better, and we should be doing it like this. I mean, even so, I think the rest of the kernels are configured, so they take the which they take account in the masks. Yeah, it's better if it doesn't diverge, because yeah, it will be more efficient overall like this, I think. It's fine. Okay, so this way it wouldn't diverge, and I think that should be the more efficient way. Even though the warps might be operating on different vectors, once they're here, we want the single instruction multiple data paradigm to be obeyed, if possible. I mean, it's not being obeyed here, and that's one of the issues. But it will simply be too complicated to... Okay, never mind. Let's just continue this. It's fine to at least... it's fine if it never just here. It was just be too difficult to check for whether the update needs to happen everywhere. And the reason why we are doing the value thresholding is because we are not actually sure which value needs to be decayed. If we didn't do the thresholding, then we'd have to decay all of the values, and we are only updating the value array for the action that has been selected. The other values can stay as is. That's why we are doing the thresholding here. It's kind of a special consideration that because we are in a parallel setting. Yeah, the thresholding is, I think, a pretty good contribution to counterfactual regret algorithmics. So, okay, if b is greater than the value threshold, then... Okay, in all, if b is greater than the value threshold, then value threshold divided by b, else 1. And what we'll do is simply a times d, b times d. And if you inline this, you'll see that we're just multiplying by the value threshold and dividing by the b. And okay, this thing here, we can just replace this with... if we write it out in full, it will be value threshold divided by b. And these two cancel out. So we can just leave the value threshold. Oh no, wait, we cannot, because, it's not just this part, but it could also be 1. Sorry about that. Yeah, like this, simple is best. Now we have the value. And these are the way that we're going to be doing the updates. That is the average policy to make it global. Grid-wide, not global. Okay, let me just do a little pause here. Let us resume. Programming really does activate my metabolism. Okay, this update... You know what, let's get rid of it. Current average value. Now local fun current average value zip current zip average policy current actually average current, and the update is 0. And that's why I removed it from here, because I don't want to bother going to zip it. Value, yeah, value is just the value. We don't need anything special. Okay, not bad. Whoops. And let me just put this here, like so. This is the way to do it. Oh, now it's readable. Just a second. Here we have the L1 normalized, but what if the sum is 0? If the sum is greater than the threshold, I mean, if the sum is 0, it will never be greater than the threshold. So it will just put 1 here. Oh, I see. I'm just wondering, I mean, could we use this kind of thing like here? If sum not equals 0, then x divided by sum, else the inverse linked. No, not really. It's kind of, yeah, it kind of irks me that it's like this. Yeah, but regret matching does need to return a valid probability distribution, unlike L1 normalized. I don't think row map. I mean, what will happen in local reduce if a particular warp is disabled? I mean, we should just skip it then, I think. Oh yeah, I mean we're going to have to test these kernels to see how they handle themselves in the face of warp divergence. I never really tested that particular aspect out. It could cause errors. To do test if local reduce. Oh damn, this really is a lot of work, isn't it? But I don't know any better way of actually implementing a poker game than in Spiral. It's kind of a pity that we have to do all this, but it's also an opportunity to get better. Okay, we don't need to decay the value arrays. We're going to be using thresholding. So let me just take a look at block scan. I mean block reduce. Block reduce to the... Yeah, I think this is what I've been wondering about. Oh, we still haven't... Yeah, it creates a label partition. Okay, I think this should work, but what about this? Index warp, loop project, share lim, warps in block. Threads per mini block, threads per warp. Okay. And this is the warp ID, this is mini block. All the warps. Thread count, threads per mini block. Yeah, okay. Yeah, okay, I do get it. I think, yeah, this should work. The way this works is that the warps store the intermediate results into this two-dimensional tensor. And this shared tensor is 2D. This one is the mini block ID. This is the warp ID. And then this warp ID, the second part, can at most be 32, and usually it will be significantly less. So after the threads load the data, the individual threads of the warp load the data or the neutral element, then they do a reduction here. And if a particular mini block is disabled, like it would be if the if the is update here is false, then I mean, then the shared tensor here, I mean, then no computation will be done. At least then that's how it should work. And now that I realize, now I realize something. This barrier CTA sync, I did a very good job with it, because if I try synchronizing the whole block here, then if I synchronize the whole block, then this kind of divergence would end up causing a deadlock. But since I'm not synchronizing the whole block, but just the mini block, this is what will enable this to actually work. Back then I only did this as a performance optimization. I didn't realize that it would also cause that this will also enable granularity at the warp level. And I think the scan works the same way. Let's see. Block reduced to the block exclusive scan. Yeah, we're using this barrier CTA sync. Yeah, it's beautiful. Yeah, we got luck here. Of course, we'll have to make absolutely sure that it works, but yeah, it's actually not that easy to make sure that everything works as intended here. You know, getting all this to actually run properly will take some luck, I think. It's kind of, it is hard to test things in Cuda. But our functional way will show us, will get us to the end. Yeah, there's so much new stuff here that needs to be tested. We're not going to be done with this very soon. I wish I could just put this like here, but I can't. Okay, I think this is pretty good now. Oh wait, we're going for down, but this thing shouldn't be run outside the loop, not here. Oh, that's a pretty serious error. So, do you understand what's going on here? It's going down to the trace, and it's accumulating the value updates and the policy updates using atomics. I mean, do we need this value update here? Trace update value. I mean, that's just the reward. Okay, we're kind of setting it into global memory instead of. Oh yeah, I was wondering what we missed. In addition to having to make this, what we are missing is the primitive to use this in a grid-wide or device-wide fashion. This one works only on a single block, this raw map, right now. And we are also missing the path probabilities. Once we do those two things, the CFR update will be complete. Of course, we'll have to actually test it after that and integrate it into the game. So yeah, we do have a bunch of work ahead of us. So how do you want to do the path probabilities? I mean, okay, you know, accumulating the path sampling probability is not hard, but how will we accumulate the probabilities for the two players? Divide by the sampling probability and multiply by the opponent. I mean, okay, I'm going to have to think about how exactly this should be done, and I need to have breakfast anyway, so we'll resume after that. I'll see you in a few moments. Okay, the break is over and it's time for us to do some more work. We're going to think about the path probabilities here. Now, what are the path probabilities? Well, I mean, do I want to draw something here? Let me give it a shot. Imagine we're going through the game and we sample a call action with 30% probability, a raise action with 50, and another raise with 70. So the path sample probability in that case will be the multiple, the product of all of these actions. But for example, the actual policy probabilities might be different. We could instead of sampling this, we could be sampling the call actions randomly, for example, and okay, this is not random, but suppose we had some kind of sampling policy to maybe encourage exploration. If our actual policy is telling us to maybe fold and call a lot, we could have another policy that calls and raises a lot, and the program would run according to that sampling policy. So suppose the actual policy is instead something like so here we have the path sampling probability, and here we have the path self probability. We can during the program runtime we can select the actions from the sampling probabilities, and we can keep note of what the actual policy probabilities are in a separate variable, even though we aren't selecting from it. For example, the sampling probability tells us to excuse me, I set up the keyboard. The sampling probability tells us to select a call action with 30%, and we do that. but the cell probability tells us it should be with 70%, so we just note that down. And as we go through the game tree, we keep note of these probabilities, both of the sample probabilities and the cell probabilities. So if we want to get, we can also have something like this, except for the opponent, but never mind that for the time being. So if we want, so once we have these path sampling probabilities, we can make use of that to do important sampling for the actions for the policy update, or the update policy in this case. So what we have to do in order to get the actual CFR update, we have to basically factor out all of the sampling probabilities. Basically factor all of that out, and then the actual probability. Okay, first of all, let's just assume something for the purpose of this discussion, that path self probability equals path path sampling probability equals path self probability. No, not like that. Sorry, it's kind of I kind of want to explain what the CFR update is, because if you look at the enumerative CFR paper, you'll see something like value minus expected value. That should be obvious what it is, but you'll see something like the opponent probability times this, and this will be the enumerative CFR probability. And the enumerative CFR probability doesn't have the sampling probabilities. Since it's doing a depth first search, all the path sampling probabilities are always 1 everywhere. And in order to actually get the, if you wanted to get the full path probability, you'd have something like self probability times the opponent probability times value minus expected value. And this would be the put in enumerative CFR. This will be like the full probability of that particular path. But what makes this counterfactual update is that it eliminates this left factor. In fact, this entire update, this is equivalent to what you would get in policy gradients, in actor critic algorithms. But that's something that's key to understand. But counterfactual regret is different, because it doesn't actually consider the self probability of the nodes that it doesn't consider the agents past the nodes that it selected. So for example, the way that this works is, imagine if it had some zero probability, for example, for calling, but that node would still get sampled or enumerated in, and then imagine if you're doing something like an actor critic algorithm. I mean, okay, over there you wouldn't even be able to select that node, but imagine if you did, then because of this self probability, the actual update would be 0. Which is kind of meaningless. And that kind of thought experiment reveals to you that it doesn't really make sense to actually consider the self probability. You can get better performance by eliminating that data point. And you only need the opponent probability. And why do you need that? That's because the opponent probability is not really the opponent probability, but the probability of the environment itself. think of the cell probability as your own probability, the one that you control, the probability in the agent, and the opponent probability is the probability of the environment. So of course you need to consider the probability of the environment in order to get the correct results. For example, you cannot assume that, for example, the opponent will always be calling or raising. That's what I'm saying. The opponent has an actual strategy that needs to be factored into the update. And when you are using a sampling version on the algorithm, you have this you have the paths that are being taken, and you have the path sampling probability, and then you divide by this, and then if you had something like self probability times the opponent probability, then this would be basically the actual path probability had you been, if you were using the actual policies and not some sampling policies. Now you need to, now you can just eliminate the self probability, and yeah, then you just get the tabular, the tabular update for the sampling counterfactual regret algorithm. So we're going to name this as path opponent probability. But it really should be named the environment. Okay, path environment probability, like this. And we could maybe we could just move it like this. It doesn't really matter. It does, but so yeah, this is one way of doing it. I think another way of doing it is to, because the okay, what I want to say is that this is one way of doing the Tabular CFR update, but I think even though I'm kind of a bit unsure right now, but because the sampling probability is really implicit, like the sampling probability is the path that's basically been selected, and we're kind of offsetting it here explicitly, and then dividing by it, and then multiplying by the environment probability. And what I wanted to say is that instead of doing that, we could do the path self probability, and this is kind of this is basically the self probability that I wrote before, but this won't be correct. And the reason why it won't be correct is because the opponent might not be using its own policy, but instead it might be using some sampling distribution. So that's why this is a problem. And this could be correct if the environment, if you're just running the simulator directly and the opponent is using its own probabilities. But we're going to be running ensembles, so it's pretty much never going to be correct. I think I implemented it like this in 2021, and yeah, back then both of the players were using their own policies even for exploration, but that won't be the case here because we'll be using because we'll be using ensembles and keeping track of we'll be using ensembles. Each of them will have different policies, but we'll be selecting action for only a single exploratory sampling policy, which will be separate from the player's policies. For exploration, we might just use the average policy For example, we might pick one of the average policies at random from each of the agents in the ensemble and then pick an action from that. So that won't be correct, and we're going to have to go with this. The environmental probability divided by the sampling probability times this. The only thing that this really worries me is, okay, for poker it doesn't really matter either way. We can just calculate this path sampling probability. But if we had something like a pretty long game, like it could be arbitrarily long, then this path sampling probability would become very inaccurate. You know, when you multiply probabilities, you're constantly multiplying numbers between 0 and 1. So one option as to what we could do is make this a log of the path probabilities, and then we could use the log probabilities and then then take the exponent on them. And you know that log a minus log b equals a divided by b. I mean, okay, let's take a look at the log identities, log formulas. Log identity. Oh yeah, here's the log identity, and log x where y is log of x minus log of y. That's what I'm doing right here, because we were kind of dividing two probabilities, and if we're using the logarithm instead, we have to subtract those. So yeah, maybe that could get us more numerical stability. In fact, I'm not really sure. I mean, this is just a trick that I've read about, but I haven't really, explored the numerical stability implications of this. So for a little bit, let's just let's just ask Bing about it. Is adding logarithms more numerically stable than adding log probabilities more numerically stable than multiplying? Let me explain why. Okay, multiplying small probabilities close to 0, the result can become extremely small, leading to underflow, loss of precision. Conversely, multiplying large probabilities can lead to overflow. Because the sum of log probabilities remains within a reasonable range. Logarithmic addition versus multiplication. Really? I mean, okay, I admit I didn't think about using them in a softmax. I mean, okay, in a softmax you're just summing up the exponents, so I don't see what log probabilities could Okay, let's chat with Bing for a bit. Yeah, I mean, okay, speed is one advantage, simplicity. Okay, what the hell is going on? X. Okay, I have no idea what the hell this is supposed to be. But yeah, that's kind of an issue with Wikipedia math articles. Oh, log returns. Yeah, I'm kind of wondering how those could work. Yeah, but returns can be between -100 and any arbitrary positive number. Huh. Yeah, so you could make -100 equal to like 1%, and then no, you can make -100 equal to the zero probability and everything else. I mean, no, it wouldn't work. I don't know. I'm going to. As to how you could represent stock prices, this is not something I'm familiar with. I read that it's better to use a logarithm for them. Oh yeah, I mean, yeah, I'm kind of being retarded. I mean, all of you have probably seen a chart of stock prices in logarithmic form. I mean, that's how it's represented. Okay, so in fact, we've used path probabilities in logarithmic form. I mean, I've used them back in 2021. Okay, and what I think, just for the sake of, we're going to use the logarithmic form, and we're also going to use 64-bit floats to represent the path probabilities. For once, we're going to kind of break away from the tradition of using 32-bit floats for everything, and we're going to be using 64-bit floats for this. And we're going to be converting them to 32-bit. Like over here. Now, we don't want to use 64-bit floats for a lot of things, and the main reason is that, okay, let's take a look at the compute capabilities. 8. Streaming multiprocessor, 64, floating point 32. 128 float. Okay, here it says 64, floating point 32, cores for single precision arithmetic operations in the white capability 8.0. and 128 in devices with compute capability 8.6, 8.7, and 8.9. My own GPU is an RTX 4060, which is 8.9. And here it says 32 FP64 for compute capability 8 and 2 FP64 of compute capability 8.9. So basically it has 128 floating point 32 and just 2 floating point 64 cores. In other words, it doesn't have much capacity for processing 64-bit values. So they should be avoided whenever possible. It has a bunch of tensor cores, 16 special functions for single precision, floating point transcendental functions. Okay, does this mean that it doesn't have double precision transcendental, special units? And these cores are just for double precision arithmetic. Okay, so I guess we should be avoiding transcendental functions with 64-bit floats. Okay, it's good that we know that. So we're going to be converting them to 32-bit floats and then taking the exponent. Makes sense. Of course, yeah, I think honestly, we should be just doing arithmetic with 64-bit floats for maximum performance. We're going to follow that rule. So, okay, no problem. Now we need to get the actual path probabilities from somewhere. And they should be in the trace. Where else would they be? Sequence ID, reward. Here's calculating the updates. Trace. Okay, where is the trace being used? Trace actions, trace update policy. Yeah, I guess it should be in trace actions. We have the action sampling probability. We also need the path probabilities. Action sampling probability. Okay, let's do path environmental probability, and this is going to be a log path in log path environment probability, log path sampling probability. And we also have the log path cell probability. And we only have the environmental probability because we have access to the entire simulator. We're kind of doing heads up no limit hold'em. We're doing a poker game with the ensembles and multiple threads, and we have access to all the probabilities. And because we can use a sampling distribution instead of just using the simulator directly. That will make optimization a lot easier. Basically, I wanted to talk about this, but it's very embarrassing that I failed in 2021, even though I've been long aware of something. Making the poker game, like like we have here. This is actually the hard part of intelligence, modeling the environment, and we're kind of giving that to the giving that to the machine learning model, and because we have actually done the hard part, it really makes zero sense that we should fail. So this time around, I want to make sure that this doesn't happen again. The game itself, that's the actual intelligent part. Well, once you have an environmental model, it should be fairly trivial to actually get intelligent behavior. Yeah, it's very pitiful that I couldn't do better. So that's why I don't want to have any more regrets. That's why I'm doing all of this again. I mean, if you didn't have the environment, and if you didn't have such a flexible model already implemented on the GPU, if you didn't have a perfect model and a perfect simulator on the GPU, then if you wanted to use counterfactual regret, we'd only really have this path self probability. Instead of dividing by the sampling probability, this would pretty much always be 1, and this would also be 1. So we'd just be dividing by the self probability to offset those, I think. Actually, no, we have the path self sampling probabilities, in fact. So we'll be dividing by the path self sampling probabilities to offset those and multiplying by path self probability. For fuck's sake, I'm just getting confused here. Okay, never mind. I won't try to figure out right now how do we do it if we didn't have access to the actual path probabilities that we need to implement CFR. Instead of wasting your time with this meandering, let's just do it the way it should be done. I have some dust in my pocket. I mean, some crumbs in my pocket. Okay, now we have this. And we need to get that from somewhere. So, okay, okay, let me just think about this. Okay, because we have the action probabilities in float 32, we could turn it into a log, and then I mean, we could turn it into a log and then float 64 without really losing anything, I think. Okay. Maybe it would be better to just... Okay, never mind that. We need to figure out... okay, this is... I guess it's incorrect now. We have the get action. Oh yeah, because we aren't actually putting the path probabilities into this. So, let's just... take a look at the get action. Get action. We get the probabilities. From what exactly? From the current policy. So, in fact, this is the action probability of the policy. So yeah, and you also need the sampling probability, action ID, and the probability. This is the action sampling probability. Oh yeah, that's fine. And we later correct. I mean, because it's we're actually taking the actions from the current policy. What happens that this action sampling probability and the action probability are the same and cancel out. But it could also be different. We could be, for example, using random action selection, or we could be using instead of the current policy, we could be using the average policy, which is slower. And let's just name this policy. And we'll name this average. And this local mask regret will mask it out. Oh yeah, I actually forgot earlier that we made a mask function. Instead, when we did the apply updates, and then we did the L1 norm clamping, where was that? Oh yeah, during the model update, L1 normalize, and thresholding, we didn't. We thought that we might need the mask, but we didn't. Okay, so now we have this action sampling probability because we are not using the current policy but the average policy. This action sampling probability will definitely be different from the action probability itself. We can reason to assume they'll be the same anymore. Okay, that's one aspect. So I won't even think about right now how to get the environmental probability. We're just going to have to make something up as that number. But as the path sampling probability, don't tell me we also have to get the actual action probability here. That would be annoying. Okay, I'm going to have to pause here so I can think about how to actually get the path probabilities. It's kind of an awkward part of this sketch. In the actual program, we'd be accumulating them along the way, but over here we might just have to make something up. Let me pause for a bit. Okay, I had time to think about it and I figured it out. The ideal way to do this, and hopefully once we actually do this ideal way, you'll be able to understand what how Tabular CFR updates actually work. So as I said, we have the sampling probabilities and the actual probabilities. So over here we're also going to add one more ID. Let's add the player ID. This will be the player ID. We'll put it here. World ID, action ID, and player ID. That's going to be a part of the trace. the actual sampling probability. That's something that's the sampling probability of the action of that specific action, and we also need the path probabilities. So how are we going to do the path probabilities? Well, let's consider putting them in here. Log path prob. Let me raise the table. Exercising my right shoulder a bit. Yeah, maybe I should be doing these exercises like every 15 minutes or so, just because my hands is really itching. So okay, never mind that. Let's make this a tensor, and I'm not sure whether to put the sequence ID first or the player ID first. Let's put the player ID. No. Let's put the sequence ID first, and then the player ID. And what this is going to be is a log probability. And yeah. We also need the thread ID. And these are going to be the log path probabilities. Each player will have its own path probabilities. And it won't be just a single path probability, but we'll have a sampling probability and the actual probability. I'm not sure what to call this, but let's call this the policy probability, sampling and the policy log probability. Log path probabilities, and we don't need to put the log here because we have the log probability in the type. Actually, let's put it in here just so we don't forget. So okay, these are the log path probabilities. We have the player ID, log path probability, and now that we assume that we have these probabilities, we can make use of them. Log path probability equal tensor create. Oh yeah, player ID equals 2. Oh yeah, first we have the size thread ID, size sequence ID, and then size player ID. So far so good. Thread ID, sequence ID, player ID. Yes. Now we have the sensor. Now in get action, I guess the only thing we are going to add here is the player ID. But in fact, we don't really need the player ID specifically here, because we don't have a separate model for every player. I mean, we could have the same model used for the different players, and that's how it's going to be done in the game itself. We don't need to do anything else there. So now we also have the calculate updates, trace, reward. We also have the player ID in the trace. gather map reduce policy and current policy. Okay, let me think about this for a bit. We need to get the... How do we get to the log path probability? So we need the thread ID, the sequence ID, and the player ID. Where are we getting? Here we're getting the update, trace update policy. Trace update value is done here. Okay, so log path probability equals trace log path probability, and we're going to apply what? Apply thread index. Yeah, then we apply the sequence ID. We also have the player ID here, but we don't want to apply it right now. We actually need, in order to calculate the update, we need to go iterate over all the player IDs. So now we have this tensor. This is the player ID, and this is the policy and the sampling. Okay, so what? We're going to this here, and here we have the log environmental probabilities, and we're going to do this a bit different. We're going to sum up the sampling probabilities, log path sampling probabilities. So the way to do that is relatively simple. In all, and we're going to have to have a single thread do a reduction over that tensor. I mean, I don't think there's any other way of doing that here. Policy current and value. Yeah, what are we iterating over that? F30, this is I32. Policy current, policy value, we apply the wall ID. This is just the action ID. Yeah, we cannot, we have to basically do the reduction in a single thread here. And that won't be too hard. Oh yeah, we also need to make this F64, I forgot about that. Log probability, that is going to be F64. So I guess we're going to do a for loop from equals 0 near to equals length length of what? Length of log path probability. I mean, it's too bad that we don't have something like TensorFold, but we can implement it. And this is we pass in the 0 as the initial element. Find is, I think it was like this, and it's s plus it's s plus tensor index I log path probability. So is this not correct? Oh yeah, this needs to be a loop for. This is the policy. Here we sum up the sampling probabilities. in addition to that, we need to get the actual policy probabilities and sum them up as well. And let's name this a bit different. Logpath policy probabilities. And this is going to be a bit different. X. Actually, we're going to do it if player ID equals I, then S, else this. And that, if you think about what this is doing, let me just try to make it a bit simpler, maybe. Oh yeah, this should also be policy. X. Or it could also be done like if then else 0. So, because this is a log probability, and you have to keep in mind that the log of 1 or 100%, which is 1, is 0. So what we're essentially doing here is setting the policy probability of the current the policy. It's kind of like assuming that the policy probability of the past actions that the player has selected is 0, is 100%, I mean. And we also assuming that the sampling probability of such an action should be 100%. By doing this subtraction here, we are kind of offsetting the sampling probability. And that kind of offsetting has the effect of assuming the past sampling probability is 100%. Hope that makes sense. Maybe we could do it like this. I think this should have at least thread divergence. So yeah, I think this is the ideal implementation of this. Yeah, this is finally the version of the algorithm version of the update that makes sense to me. we kind of offset the sampling probabilities and include the actual policy probabilities, and we also assume that the player's own actions are for all the past nodes are 0. So you have to keep in mind, we don't really, it's true, in a game like poker, we only have, I mean, we have the different players, and okay, since we have the heads up game, we only have 2 players, but we might have more than just 2 players, like in a 6-man game. And we want to add all the sampling probabilities together for such games and subtract them from the policy probabilities. While making sure that the counterfactual updates make sense. And the counterfactual operation in something like a probabilistic programming language is kind of like taking some random variable and setting it to a value. And that has the effect probabilistically of setting its probability to 1. I mean, if you haven't really looked into probabilistic programming languages, this should be gibberish. But if you understand the counterfactual, I mean, if you study it, if you study the counterfactual regret algorithm, you'll see that it's like half of a probabilistic programming language. It's kind of like probabilistic programming language for just discrete distributions. Oh yeah, we haven't forgotten them, and we have them now. And okay, in the apply updates, we don't need to consider the player IDs at all anymore. They are perfectly fine. I mean, do we need even the world ID? I mean, okay, we don't need the world ID. Do we need the action ID? Oh yeah, we do need those for the updating the value arrays. So we only need the action ID and the world ID and the sequence ID. Oh, did I get anything wrong? I mean, probably not. I think I got the updates right. Oh, it's actually pretty. Yeah, it is a complex algorithm, no doubt about that. Now, in addition to that, we have to keep track of, in trace actions, it's expecting the player ID. In addition to the world ID. And we also have to set the policy probabilities. I mean, no, not the policy probabilities, but the log path probabilities. And in order to actually be able to do that, we see that in this trace here we have the log path probability, size thread ID, size sequence ID, and size player ID. And locally in each thread we're going to have just a tensor, but of size log path tensor create, and it's going to be of size player ID, and to do needs to be 0 init. Okay, we assume that this is 0 initialized for now. We have this log path probability that is set to 0. Player ID, player ID, player ID, and we have the action ID and the action sampling probability. Oh wait, I forgot this. Let's put some player IDs here, like this is 0, this is 1, 0, 0, okay. So yeah, now we have the player ID. Or here we'll also pass in the player ID. Oh, this is not correct. And in addition to that, we need to update this log path probability. So I mean, one way that we can imagine that being done is like tensor set, let's say player ID, and we could take the log log of action sampling probability. Oh yeah, this needs to be the sampling probability. Log action sampling. Probability. Policy. Log tensor index action ID. And then fucking what? We need to take a look at the model. Let's see, how is that being done? Model, old ID, action ID, and we need to get the current policy probability. Okay. World ID, action ID. Okay, where's the model? Policy, current. I mean, yeah, that's one way of getting it, but we also have to add them to the value. It's not just not just set them. Log sampling probability, transfer index, and this will end up loading all the elements in the tensor. So instead of doing this kind of thing, it's more efficient to do reshape fun x policy current. And it's not reshape but rezip. we need something like tensor add, and then we okay, let's do tensor update. And it's going to be basically plus this. I mean, it's going to be fun AB, and this is going to be sampling. Yeah, we could do it like this. A with sampling plus but we also have those stack map operations, I think, like can we do like, if you look in the loop, now do we have the like we have the map rollback, but this is a real operation. These are all in the real segment. Extract map to okay, here's what I want to do. Extract map to plus. And yeah, of course it's complaining that this is not the real segment. So real open real core in extract map 2. And the only thing we need is this tensor update. Yeah, we also need the to apply the V here. Okay, so let's go into tensor main. Okay, what do we do? Inol tensor update for all dim L I dim F L L return as unit and tensor index. Oh yeah, we also need the tensor. Tensor index at I, we pass this into D, and then we also set tensor set at I. In fact, maybe an easier way of writing this out would be to pipe it like T tensor index I F tensor set at I. No. And in that case, we're kind of short here. We only have the value, but not the tensor. Whatever. Let's go with this. updates the tensor at okay, let's also set this to 0. Loop linear log path probability dim fun I tensor set I 0 log path probability. Oh yeah, this isn't bad. I32. Oh wait, why is this like... Oh yeah, we forgot to pass in the tensor. Log path probability, I think. And we cannot set this to 0, but sampling equals 0 and policy equals 0. What the hell? Sampling log probability policy log probability tensor index as well ID policy current. Oh yeah, this makes perfect sense. Now we don't even have to wonder about where this sampling probability is coming from. It can be completely random, it could be 1, whatever. And this policy probability can only be this. We index into the model with the whole ID and the action ID and get the policy at from that array using the action ID. Oh yeah, here we are setting the log path probability, but we also need to actually set the trace, I think. We're just setting this local array here, and now we have to actually set the values in this local array to the one in the trace. Okay, so how exactly do I want to do this? Okay, let's first trace. Here we're setting trace actions. Trace log path probability. Apply. Trace apply what? Thread index. And yeah, the sequence ID, which is just I here. Apply I. Now we have this trace log path probability, and this dimension is should be the player ID. Now we have to do a linear loop. Loop linear dim fun I tensor set I tensor index I from log path probability into trace log path probability. Oh, thank fucking God. Oh, okay. Okay, now this part of the update is finally done. To arguably, do we even need like, do we even need to fucking set this? We can just do tensor update and oh no. We first need to do a tensor update player ID. We need to update it just at that ID. And then we need to actually set the path probabilities for that sequence ID. Okay, I get it. I mean, this is the best way. So, are we actually using this properly? Trace log path probability. Here it is, trace log path probability, thread index and sequence ID. Yes, this is it. Oh, thank God. We finally did it. I think this is the actual CFR update. It's kind of impressive that I did this all off memory. But I guess that just shows how long I studied this. I know the control flow inside and out for this. And I also feel this is like the clearest version of the counterfactual regret algorithm that I've ever done. Like, I think the way I'm calculating the path probabilities here is very nice. It's very, very clear. Maybe if I could do something like a local map and then do this and then a local sum, it would be better. Yes. Yes, it would be better like that. Okay, so let's do a tensor map and tensor sum. Of course, we first have to do a tensor fold in order to implement this tensor sum, but let's just do a tensor map. Tensor map, we don't have one in here, so okay. Maps over a tensor using a single thread. Oh, tensor map. I mean, we don't need the I. This is going to be from A to B. A, B, okay, this is A, tensor dim B, sorry, that ambulance distracted me for a bit. Let's do a loop linear. This is tdim fan I, and then we just do something very similar to before, and we actually need to allocate a new tensor. Tensor create tdim tensor set tensor set out, and this will be tensor index into t at I. We also need to pass it into f. Yeah, this is the tensor map. And we can also do a tensor fold. Tensor fold. Okay, this will be like S of A. S A neutral element oh god, I don't remember when there were ambulances passing by so often. Maybe there has been maybe there was some kind of a traffic accident somewhere. I remember once coming back from the town, and I saw a car that was literally upside down on the road. Hopefully, from what I could tell, nobody died then, but maybe somebody died this time around. Who knows? Okay, enough thinking about that. I need to focus. Okay, so we have the tensor fold, the neutral element, this is not the neutral element, but just the state. We have the S. Let's give it a type. S of S. Tensor dim A, and we get the S out. The only problem is that we have this fucking linear loop, and it cannot take in the state. So what we're going to do, we don't need the out. We're going to use a regular for loop. Loop for from equals 0 near. Oh crap! I just remember right now why we're using a linear loop. Because it does automatic dimension projection. So okay, so how are we going to propagate the state? Like, I guess okay, let's say I take a look at the loop and we'll copy paste some code from there. Okay, where's the loop? Where's the loop? Linear. For fuck's sake. Oh, this is more complex than I remember it. Directly in spiral. Yeah, we make this we do this thing. Yeah, so that's why we aren't passing the state. Okay, it makes sense because we have to do nested loops instead of using projections. Okay, so but if you look at how the for loop for by, so we have this I state. So what we should do is duplicate the state, loop dup I, and then use loop set to set the state to the new value. Okay, s loop dup s loop set and what? Yeah, we need to set the s to the new value. Just what am I thinking? Loop set s fs. Okay, and we return the s. Problem solved. Now we have the tensor fold. And we could fold over this tensor. I mean, this is. I mean, what I wanted to say is. Okay, where the hell is this? Let's comment this out. We'll copy it. I mean, we'll comment this back in, and we can implement this like. Okay, let's see t, and yeah, this basically this is the inefficient way of doing this. Instead, we have to do rezip fan x policy. Oh wait, log pad probability. Okay, why is this? Oh yeah, it's just expecting a unit type. Never mind. And then we do a local map. Except that now we don't have the fucking index. In order to get the index, what exactly should we do? I mean, we cannot zip it with JTensor. That's the action ID. I mean, the only thing we could do is maybe implement map_i. Okay, let's do the map_i. Fonts int oh no, actually it's dim okay, it's like this: tensor index it provides the index as the first argument. Okay, so now we can do. Wait, I forgot to name it map_i. It's still tensor map. Okay, now we have the local map_i. Fan I x And then what we just do is this thing here. What's the problem? Aha, it's tensor map.i. What the hell am I doing? Tensor map.i. Good thing that I didn't do local map.i. That would give us an error at runtime. No, actually it will give us an error at compile time because the local map is expecting a 2D tensor. So now we do tensor fold 0 plus, and this will sum it up. We can do the same thing for the other case, except we don't have to, set the wait. Yeah. If layer ID is I, then fuck. We got it the other way around. It should be like we should be setting this to 0 and everything else to x. 0 is 100% and the negative values are negative percentages. Like okay, let's open the F sharp. Whoops, not that, but I need to press Control N. Let's select the F sharp language, and if you do log 1.0, you'll see that it's 0 over here. But if we do something like 0.5, then that's a negative value, and everything below 1 is a negative value. And log of 0 is negative infinity. Oops. Log of 0 is negative infinity. And this is actually a very nice way of doing it, because if you I'm adding a bunch of log probabilities together, and one of them is 0%, which is negative infinity in log form, then the final result will still be negative infinity. It's like multiplying a large number, taking a product across a vector, and one of the elements is 0. Then the final result will also be 0. I mean, unless some of the values are nans or something like that. In that case, the final result will be nan, but in regular cases, it would be minus infinity. I mean, the guys who designed the floating point arithmetic knew what they were doing. Apart from the fact that nan equals nan is false. Okay, that's fucking garbage. Okay, doing it in this form, using a tensor map.i, does allow some instructional level parallelism that wouldn't be there if we just did a loop like this. Oh wait, and here we need the X sampling. Oh my god, how many errors there were, it's amazing. So I player ID equals I, then 0, else X. Yeah, it's good. It's great that we caught that in time. And this is what makes the update a counterfactual one. It's kind of taking a moment in time and then looking back and imagining how things would be if the probabilities of something taken were different. It's kind of like thinking back to some event and saying to yourself, how would it be if I had taken this or that action? I guess that's why the algorithm deals with the regrets. nice. Yeah, I'm very pleased that I actually took the time to do this kind of refactor. Tensor mapI, TensorFold. I think maybe it wouldn't be bad if we instead of calling tensor map, we could just call it map and mapI and fold. Map over a tensor using a single thread. Yeah, this is fine. Tensor M, but I'm going to prefix it explicitly. So this, if we end up importing something that has fold or mapI in it, we don't want this to break. Oh, this is extremely good. And the way this algorithm is written right now, it will work for when we do. I mean, if we do something like 6-man games or 9-man games, or on pretty much any poker variant, we'll just sum up the log policy probabilities like this. Logpath sampling probability, logpath policy probability. I guess this is the only thing that we still need to do. We need to make this map. We need to make this raw map use the entire GPU. I mean, there's no way around it. I mean, what about all of this? Like, I mean, okay, this is thread specific. Yeah, we're applying the trend index here. But the thing is, this will in the future. This should be the trend, the ID of the thread in the grid, not the ID of the thread in the block. But as far as sketching out how tabular CFR should be implemented, this is perfect. And I think it might not be a bad idea to maybe end the video here. It's like, it should be at this point like 8 hours long, so... what's this? If second A equals action ID, second B action ID. here we're just finding the probability of the action ID. Wait, what the fuck? Oh yeah, yes, yeah, it makes sense. We cannot just index it into this to the tensor. We have to do a reduction checking for the ID. I mean, we could also do something like create a shared array and then put it into the shared array and then index into that. But then, no, that won't be good. This is like this is a row gather operation, so yeah, we cannot do anything like that. We cannot share stuff in shared memory. I think this is actually the easiest way of doing it. I mean, we have this mask, the RNG, world ID, player ID, action ID, sequence ID. Oh, we have the log probabilities. I think I'm feeling pretty good about this. Okay, we're going to end this video here, and in the next one we are going to move forward towards the actual implementation of this. We're going to make sure this tabular CFR thing actually runs on the entire GPU, and we're also going to test it out and see whether it all compiles and runs properly. As far as simply sketching out the solution goes, this is perfect. I'm very pleased by how this looks. I mean, if you bother to actually read this, it shouldn't be too hard to trace. And you know, you have this video and you've seen me implement it from scratch, so hopefully that will kind of give you the flow, the sense for the flow of things. I mean, the only thing I should do is maybe leave some comments, but I mean, the comments would just make it less readable, in my opinion. If has been updated. Yeah, I'm kind of struggling to think what makes this so good, and what really makes this so good is that we are kind of using functional programming operations like local map, local sum, and so on. And over here, when we're calculating the log probabilities, we're using map and fold. This is what makes this pretty good, in my opinion. The tabular CFR that I did in Cython wasn't anywhere as close as elegant as this. Yeah, we're done. It's 4:15 p.m. I'm going to add this final bit to the timeline and do the audio processing and set it to render. And then we are going to continue with the next part tomorrow. See you there. Bye bye.